this computer. Perfect. Just wanted to get, where's my share screen? Okay, good. So let me first say a couple of words on myself. About myself, I'm Professor Adnan Ibrahimbegovic, what we call Professor classe exceptionnel in the chaire de mécanique et membre of Institut Universitaire de France. I've been at UTC since 2014, and right now went through all this sequence of what you call it a usual path for a professor. So before coming to UTC, for 15 years, I was at École Normale Supérieure in Kashan, in the Laboratory of Mechanics and Technology, part of one of these sections. And basically, when they came up with the SACLI project, at that time, it was still very early on. It's like only 10 years later, the SACLI project is getting sort of together. So I thought there's like too much of time waiting of doing that. Basically, if you're not familiar with SACLI project, this is under the impulse of this ranking of the higher education that France decided to merge together these universities, which theoretically were very small schools in engineering profession. So basically, one of those projects was merging all these historical schools, École Polytechnique, École Centrale, École des Mines, École Normale Supérieure, and so on, into a single school, and joining it with University of Paris-Orsay. So they turned this into Plateau Saclay to call it Paris Saclay. And it took really a long time, as far as I know. Even today, École Polytechnique is still not completely in. Nonetheless, at the same time, there was a merging of University of Pierre Marie Curie and Sorbonne. They took the name of Sorbonne and they put a S, like a plural, and they asked University of Technology Compiègne to become engineering college. So that is the reason I was offered the chair to sort of merge different engineering disciplines into putting together sort of works from civil engineering, mechanical engineering, electrical engineering, and so on and so forth, which is really the path that our laboratory has followed. 1 year after that, I got a chair in something called the Institut Universitaire de France. This is practically the same thing as the Collège de France, if you're familiar with that. The only thing, the difference is that professors who are appointed there are only 40 of us, are actually put in their own school so that they can kind of strengthen the research in their own school. And that happened really in a kind of nice way, at least for me, also for UTC, I would say. This way, the only thing I'm teaching is actually this doctoral school. And basically, this is the course I'm teaching, and this is the type of topic. If you're really interested beyond this course to have some kind of interaction with me, basically, there was lots of different topics we studied. And there's a number of doctoral theses already defended, 46, and the postdocs 11, and 3 habilitation. Habilitation is the degree when you have to do after you've done your PhD. This is the degree that you need in order to become professor. Without habilitation, you cannot become professor. So basically, there's lots of them who have completed PhD, some of them habilitation. And right now, I would say the summary of all that is there are 12 different countries where my former students are professors, number of French industry partners, and so on and so forth. So basically, right now, there's 7 different projects with a postdoc and several PhD students. Most of these PhD students are co-advised with their colleagues from different countries, as Croatia, Bosnia, Germany, Brazil, and so on and so forth. So basically, in my work, where I actually try to merge different disciplines, I really like collaborating with many different colleagues. So doing a thesis is really something that is learning experience, not only for a student, but also for advisor. And so we have really benefited from collaboration with the people in USA, Canada, Germany, Slovenia, Hungary, Czech Republic, Croatia, Turkey, Bosnia, Spain. And actually, if you have a situation where you have a 2 thesis director, it's not actually a disadvantage. There's actually something that I found because my chair was for innovation. So I said, okay, what is the essence of innovation? They said it's a creative pairs. So at least you find one person to whom you can discuss and really have all the details and try to convince this person. If you manage to convince this person already, you have something that you're kind of winning. They'll compare this to famous group Beatles, so they have John Lennon and Paul McCartney. And so these guys were creating wonderful songs. And they say, even if you're Ringo Starr, that these two guys troubling you, they still bear on. So I hope you're in the situation where you have like a very good advising team and your thesis is going quite well. Basically, the other thing that we have in terms of interaction, I'm trying to organize a series of conferences. So the overall, let's say, domain, which covers most what we are doing, is really as concerns solids and fluids. And so there's a series of conferences on entitled Multi-Scale Computation Methods in Solids and Fluids. And then there's a similar conferences that we've done in a collaboration with South Korea. I had a long collaboration with KAIST. This is a sort of a SACLE of South Korea. So what I'm really teaching here is in also presenting different books. So right now there's something like 10 different books that you can consult. Some of them I wrote, some of them I was a co-author. And basically there's a number of papers. So we'll probably try to make something like a specific paper which is very close to your PhD topic. So this way I can give you a chance to show me how you can go really very deeply into the paper as well, rather than just the basic knowledge. Because the goal of this course, in my mind, is really strengthening the muscle of all of you who are doing PhD thesis. Basically, when you're doing engineering studies, you are really kind of very strongly conditioned towards, let's say, doing lots of exercise session. However, when you actually have to do a PhD thesis, you have to come up with a different theoretical development yourself. So in order to be able to do that, you have to strengthen your theory. So learning how to read the books, to read the papers and get something out of that is a really very important part of our profession, basically. So this course was taught in many different places abroad, in Asia, in Europe, in Latin America. And basically, this is one from the KAIST, where I was teaching this Korea Advanced Institute of Science Technology. And this is the best school in Korea. Basically, we have 5,000 students who are paid all the way until the PhD thesis, the end of the PhD thesis. So it's really like a top of the crop people. And so that really gives you a chance to kind of perfection the school of this kind. But it wasn't only Korea. As I said, there's like 29 times since 2000, we taught it in different places throughout Europe, in Asia. There was Turkey, India, and then in Latin America, it was Brazil, Mexico, and so on and so forth. So this is also the course that I've been teaching now already 9 times. Now this is the jubilee. This is the 10th time I'm teaching this course. It was actually the first course which was created as a scientific course in École Doctorale. And I'm glad at least some of them could benefit from this type of knowledge. So basically, the book of this course, there's a French version, there's English version. So as I know, you have both. This English version is also available electronic version. I'm not sure about French version, but I know there's since the book was nominated for Robert War best university textbook. I think I had to give 10 copies to UTC, so they probably have it enough in the library. So whatever I'm not explaining in detail, I will refer you to these 2 books to kind of check a little bit more. The schedule that I suggested is it was supposed to be in Amphigao, so that we needed like half an hour. That's why I shifted to 8:45, 10:15, then 10:50, 10:30 is a break, and 10:30, 12. We'll do that every morning starting today. So basically, what we are covering is, I'll actually do this first lecture nonetheless to get you used to it because it's very important. Once I kind of skipped and then I was kind of disappointed with the result that the basic notions like explain the first chapter are not really fully mastered. After we mastered like the basic notion, the simplest context of one-dimensional theory, then we go to 2D and 3D problem, where actually in the essence, by using the tensor notation, you actually realize that you have the same type of problem you deal with, but there are many more details. So it's essential to have a good notation and to have something which is really giving you a chance to move very quickly through this in order to be able to efficiently cover the whole domain. Then behavior of elasticity is not typical for many problems we are interested in. We are much more interested in the inelastic behavior. What that means, when you move beyond certain limit of elasticity, there are some consequences to your material. It never comes back to the original state. You have typically something that goes on in the wrong way, either plastic deformation or cracks or whatever. And that, to fully understand what's happening, in this case, you actually have to master thermodynamics. Thermodynamics is the first multiphysics type of domain, which is the best understood nowadays, which is mixture between heat transfer and mechanics or dynamics. So once we have mastered this with the simplest models of elasticity, basic plasticity, basic damage, and so on, we can go to more advanced models where you can combine those things and get something which is more, close to the real behavior of the materials of interest to us. And then basically we can mix this with different domains. Sometimes I mix this with electromagnetics when we have people who are studying in the branch of a laboratory which deals with electrical engineering, which doesn't happen to be the case this year. So I might skip that unless you are interested, we can cover that as well. And there's actually a new book coming this year about this topic. And then we'll do the multi-scale modeling, which is really very pertinent today because that gives you the most predictive knowledge of behavior of material, because at the fine scale, the situation becomes a little bit simpler and you know what to do in that sense. And then we move to the large displacement, large deformation. This is when you have very large motion and very large deformation, which is typical of many materials, typically structures and systems. After that, we cover maybe problem interaction, fluids and structures. And then, of course, the problem with stability, and then a multi-body system and so on and so forth. So basically, this is the kind of rough outline that I had in mind, but it really depends on our interaction and how we're going to go with that as we go along. So these are these books either in French or in English. Also, it's translated in ex-Yugoslav languages, at least half of that. And Spanish version keep coming. It hasn't been written yet. Basically, a colleague of mine from École Normale Supérieure de Cachan, which is even today the most well-known professor in mechanics, he said that basically in a book like that, we covered a lot of things. And he said that it was done by restructuring the presentation, merging European and North American school. I think what he means is in France, if you have been through a typical undergraduate education, at least what I could see at the École Normale Supérieure de Cachan, these are courses given to Normalian. The people start immediately from a very general model, 3D motion. And then basically they cover a lot of time just simply discussing what exactly they're talking about. I like starting the other way, which I saw that we were doing at Berkeley, where I did my PhD thesis. You take the simplest possible model, you understand that one, and then you start generalizing more and more. So for PLDs, this has to be like something that you're merging these two together. In any case, the book itself was really handling very well. It was 25% top sales of Springer, because in this domain, you don't have too many of these books. Typically, people write papers. I had to write a book because I always had lots of PhD students, and I realized if you work with one first-year PhD student without a book, you spend all the time just teaching the basic things. So this way, with the book, a student has the chance to progressing much faster. Basically, that was really my duty to that. Myself, I was educated in former Yugoslavia, then at Berkeley, then in Switzerland, and in France with habilitation. And basically, I really don't remember anymore where I learned something, because going from one place to another, change 4 countries, 5 different universities, you really end up learning a lot. So the merger of all this that we need for this type of knowledge is first knowledge of materials. That means what kind of material we're talking about. Especially in mechanics, we have now a large diversity of composite materials. So you really have to know what you're talking about for specific material to be able to fully characterize behavior. Then thermodynamics is really, as I said, the best basis that allows you to do a solid basis for providing the estimate of dissipation. Basically, what characterizes inelastic phenomena is the effect of dissipation. So thermodynamics gives us very rigorous definition of dissipation, which we will cover. Then it is solid mechanics, which actually is giving you the basic equation of mechanics, and especially the kind of formulation that we want is a variational formulation on which we base our solution method. It's called finite element method. Finite element method in rough is nothing else but dividing a very complex domain into a certain number of subdomains and then focusing on a particular subdomain only. And as we go along, we'll see how actually it works. And now you end up, whatever you do with a set of algebraic equations, it could be linear or it could be nonlinear. So for that reason, you need some kind of notions of applied mathematics, numerical analysis, functional analysis, not because you need mathematics badly to study existence, uniqueness, and so on and so forth, but you need a rigorous definition because with the computers, you have to be rigorous to know what you're doing because computer doesn't think, they just reproduce what we tell them in our programming language, whatever that language happened to be. So this is the structure of the book. I really managed to cover in only 600 pages, lots of notion, which pertain to plasticity, damage, large deformation, contact dynamics, instability, localization, failure, discrete models, multi-scale model, multi-physics, and parallel computing. And basically, everything is kind of oriented towards the finite element solution method, which for solid mechanics is the method to be used. All the commercial software that really are very much used by profession are based on the finite element method. It's a little bit different in fluid mechanics, where they have a large diversity of different methods. One of them finite element, but they have to be stabilized, but they also have finite volume, which is kind of simplified version of finite element with a constant rating function and so on and so forth. They have spectral method. And because in a fluid, the interest is somewhat different than the solids. In fluids, it's really like a conservation properties and things like that, whereas in solids, the most, let's say, touchy behavior is really constitutive behavior of cellular material. So in order to make such a huge domain more, let's say, structured, I said what we are doing all the time, we are solving so-called boundary value problem. What it means is that you take a very complex structure and you take part of that, a single component that is the most interest to you. And then basically say, in order to reproduce what this component is undergoing inside the real structure, you have to put so-called boundary conditions. So in mechanics, where the fields that you compute are displacement, stresses, and strain, typically the boundary condition pertain to the value of displacement and stresses. So either you impose displacement or you impose the stress. You always have to impose a certain number of displacement in order to remove what is called rigid body motion, where the structure can simply fly off and you cannot then consider that to be a structure, just a flying object. So basically, in the boundary problem, you have always three types of typical equation. You have a kinematics, you have a constitutive equation, you have equilibrium. So I start the book after introduction by taking one of these equations being nonlinear and doing elaborate analysis about that. And then the last part is when you have a boundary condition to be changing. This is so-called contact problem. Again, you start analysis about that. After this basic stuff is done, this is called statics. You go to dynamics. In other words, where you have a time dependency on the loading, which produces a time dependency on the displacement and so on. So basically, for that one, you need not only finite element to discretize in space, but you also need a time integration scheme to discretize in time. And then I go back to thermodynamics that I already used in chapter 3 to explain inelastic behavior. By this time, I let both of these to be a non-stationary. That means you have a non-stationary heat transfer and non-stationary mechanics rather dynamics. And then you show how you actually compute the solution either sequentially or globally in a single shot. And then if you have a nonlinear behavior, you might go into instability. What instability is if you have a very small perturbation in terms of the loading or the source that you put on a structure, and you have disproportionately very large response, then you might be undergoing instability phenomena. And that's also something that you should be avoiding. Typical examples are flutter your airplane wing if you've been in turbulent front. Recently, there was actually Boeing 737 MAX that the part of fuselage fell off. That really makes you not to want to take a flight with the Boeing 737 MAX. Or you have like a famous disaster with the bridges, Tacoma Bridge. It was never really taken into account the strong winds, lateral winds on this bridge. So when they built it, they put it in the circulation, and the strong wind came, and they go into this really very, very large instability, flat instability of a bridge, and the whole bridge collapsed in seconds, basically. It was a really wonderful video that I found recently. I mean, it's wonderful to see. It was certainly much less wonderful to be on the bridge, but it was collapsing. And then finally, the last chapter is about multi-scale methods, because It really is, that's where the present research comes. So I would say the book is a kind of good level of really starting dwelling into the doctoral thesis of the present day, with the last chapters, which are certainly of interest for those who are already working with. And hopefully you will be able to get this book. If you are not able, let me know, and I can certainly try to help you with getting the copies of this book, and so you can follow fully the course I'm giving you. If I look a little bit more in detail, here's a typical type of structure. As I start with the 1D problem, and I present all this, and then I go to the 3D problem, where the goal is really with the proper notation, which is here tensor notation. I can show that in 2D, 3D, we're not inventing new mechanics. We're studying the same mechanics. It's only that there are many more components. And for that reason, you need like a little bit better notation. Then in the inelastic behavior, again, I start with any problem because it allows me to give you fully illustration how you actually do the computation. You can do some hand computation to be able to understand fully all the details. And then I show the 3D model, which is the first one that is historically the most important, that is for metal. It's so-called for Mises model of plasticity, J2 plasticity, which happened to be also only one mechanism, which is really shear deformation, which goes wrong, and then you go into plasticity. And after that, you can do different refinements rather than inventing a billion of these different criteria, which will come up today. I just show in this basic model how to improve the predictive capability by adding nonlinear isotopic hardening, kinematic hardening, rate dependence plasticity, multi-surface plasticity, and so on and so forth. Plasticity, which has nonlinear elastic response. And then plasticity is just one version. Damage is another. Plasticity is about getting a residual plastic deformation. Damage is about changing your elastic modulus properties because of the cracks. And so then if you have really very complex behavior like an earthquake, where you have both plastic deformation and changing elastic properties because of the crack, then you need coupled damage plasticity. So here we actually presented how actually to merge these two together within the same framework, which was not typical of the previous development. Something like books of Lemaitre and stuff, we didn't certainly do that. So then we go into the large displacement, large deformation analysis. Again, the basic thing is only one, which is the strain measure, which was found for small displacement theory, which is infinitesimal strain, is no longer sufficient. So we need some appropriate large deformation measure. It happened to be there are many, in fact, infinitely many, and each of these deformation measures come with their own stress tensor. So you have to first identify the corresponding couples strain and couple stress, which are conjugate in terms of the work. And then basically you have to come up with a constitutive behavior. Of course, then again, in a large deformation setting, constitutive behavior happen to be certainly more difficult to find because many more things happen. In the small strain, you only have a very small strain, but in a large, you can have moderate, very large, and then materials start behaving in a very different way once you go into the very different strain ranges. So basically, the last part is, as I said, changing boundary condition with the contact problem and so on and so forth. After that, we have dynamics, time integration schemes, thermomechanics, and geometrical stability, and finally, multi-scale behavior of the material. The fact that we are merging many different things here, it's also in the spirit of time. I mean, I know that when École Doctorale was built, my predecessor, Economa Superior Education, was the professor in the Ministry of Higher Education who was handling this. He also did his PhD in US, and he knew how good it was, the graduate school in US. So he was thinking of putting 100 hours of high-level courses in doctoral school. It turned out actually came down to 35, and all the others are really courses that are sort of more practical knowledge rather than really high-level scientific courses. So one of them, as far as I remember, is how to build European project. Just to let you know, getting European project is not an easy job. Today, there's a scheme called ERC, European Research Council. I was one of the members judging the project that I presented there. They give young people after PhD 1.5 million, but you really have to have a great idea. And then they give more senior people 2.5 million. I was always joking, they should give much more to the senior people than to young people because only 1 million is too much. But what the hell, they never listen. But the thing is, when I really got into this panel, I looked into the panel structure and I saw that there are 10 of them. Today, there's a little bit more. And basically, if you look at them, they are really fundamental sciences all covered. You have mathematics, then you have like physics, then you have chemistry, and so on and so forth. And then all the engineering disciplines are squeezed into this something called the products and process engineering. Inside, you have aerospace, chemical, civil, computational, fluid mechanics, energy, mechanical material production, product design, sustainability, lightweight, so on and so forth. So I thought this is really not fair to engineers. They're not really giving due credit to what we can actually do. But in fact, they might be right, because what we need from engineers is to kind of save the comfort that we have, that we can take this course even on Zoom and even whatever is the situation outside, we have this communication, so on and so forth. Much of that is really due to engineers, that we have such a level. So merging the different engineering disciplines is definitely something that is the fact of the future. At least this is the indication for European Union. So let's go to work here and start see what we can do there. Up and up. So I will start with the simplest problem that we can study, which is basically one-dimensional problem. I took these notes from the course that we taught some time ago with my former advisor, Professor Robert Taylor, who is co-author of books in Zinke-Schleller, probably the most well-known book on finite elements. And the guest star was Professor Franco Brezzi. There's a Brezzi-Babushka conditions on the mixed problem and so on and so forth. And it was taught in Italy. So you had to have welcome Benvenuti, sorry. So here's the outline of the lecture that I wanted to cover. First, give you what we actually want to study and what is this all about, what is our motivation. Then to give you the theoretical formulation of the problem in 1D, and in particular introduce the strong form, the weak form, and variational formulation. Then to give you the basic solution procedures, how we actually solve a problem of this kind. And then we go into something that is really like a technology of the finite element method in 1D. So that's the reason I wanted to cover this again, because it's really the most important part of when you're using computer code. Unfortunately, by the time that we have available and your obligation, the other type of thing that you have to do, I did not want to introduce using the computer software, because this way I can focus on improving your theoretical knowledge, which you certainly need when you're doing your thesis. But at least I wanted to discuss this way the kind of common feature in all this software, which I call the technology of the finite element method, because they all share the similar type of thing, which is let's say the need to solve a very large system algebraic equation, which is to perform efficient building of these finite element matrices and so on and so forth. And this is all thing that we discuss in detail and give you kind of indication what is going on. So when you make a choice of the computer code of the element and so on and so forth, you have a little bit more educated choice in this way. So the motivation for that is that all the problems in mechanics that are of interest today are nonlinear. Linear problem, that means your Hooke's law is basically limited validity. And that was already the point of view of masters of the 18th century, names like Euler, Bernoulli, and so on and so forth. Today, many people, when we talk about Euler Bernoulli beam, they're talking about linear beam. In fact, the real beam that Euler introduced was certainly not linear. That was called Euler Elastica, and it was able to do very, very large rotation. There was so-called Euler angles that are describing these large rotations, so on and so forth. So basically, they were even able to obtain some exact solution for such highly nonlinear problems, but not many of them you could obtain this way. So in the 19th century, there was many different works. The probably most remarkable work of Cauchy, who actually linearized all this. So introduced linear theory of continuum model, and he introduced in the process in 3D a stress tensor, which is like a linear operator that produces vector from a given vector. So you need like a value of stress vector in certain orientation, which is given by the unit vector exterior normal n. You multiply this unit vector n by a stress tensor, which is a matrix representation 3 by 3, and you obtain 3 components of the stresses, which are acting on this plane oriented by the unit vector n. So in 19th century, there were kind of lots of these books that were able then to solve linear problems. And then for that, it's much more easy to obtain agreement. So other than dispute between Cauchy, who was selling hyperelasticity, versus Green, who was selling hyperelasticity, we have a potential. Most of the other things were really under control. But then you really didn't also master correctly the inelastic behavior with internal hidden variables. We'll talk about that in a moment. So basically, in the 20th century, the computer came into power, And then basically you needed a more, let's say, ambitious type of development. So some of these discussing, let's say, stability, instability, other works on Poincaré in France, Lyapunov in Russia, and basically their qualitative method about instability. And then probably a very influential book, probably the most influential at the time, was a Handbuch der Physik that was written by Truesdell. That was really like presenting the basis of continuum mechanics in a very, very sort of rigorous way at that time. And they, just to give indication, if you haven't seen this book, you could, for curiosity, consult that, because they've been using all kind of letters that you can possibly imagine. There's such a variety of ideas and notation that it's really not an easy reading. But the problem is that definitely these are very knowledgeable people, but they never did computation. So most of the things that they've done at that time, in particular, it's material with long memory, where you have to integrate from -50 to present time to get the stress proved to be not correct. You need rather like these internal variables. You need the evolution equation that you don't integrate from -infinity and so on, but you accumulate as you go along with the process. So these were the starting point, which were, on the other hand, quite ignored by engineers. Engineers try to do upscaling of linear analysis, or the works of Jagmai, the thesis, and Barthes' book. Barthes was professor at MIT, he's now retired. Basically, he was using updated Lagrangian formulation. When you have a large deformation, you can keep moving the frame in each increment of the solution, and you pretend that in each increment you have something like a linear theory, which is one way of treating the problem, but of course limited in terms of validity. Similar to updated sort of co-rotation formulation. It was invented by Argyris in the 70s and popularized in a book by Crisfield. Basically, it's the same thing as updated Lagrangian, only it's suitable to structures where the rotation is the part how you move the frame. And then the same thing in co-rotational statics is the same like floating frame in dynamics. So it was made popular by Kane, which was a big name in multibody dynamics. And then Sheelan, who was my partner in organizing conference some time ago, he was a German leader of a multibody dynamics community. They use the same thing for the dynamics. So this way you have very complicated mass matrix and this kind of simple stiffness, and then you can compute some kind of whatever eigenmodes and so on and so forth, another side of approximation. So what is really coming in 21st century, these are the things which were prepared some time ago, so still fine. At that time, I just said multiphysics, multiscale, multimedia, that's for sure. Nowadays, I have this in the last book that just came out. My opinion about this, there's also something called artificial intelligence, where they're threatening they're going to put out to work not only administration, but engineers, researchers, teachers, and so on and so forth. So I really do not share this. I know that they can do lots of nice things in a sort of statistical way. We do a lot of that. I'll show you some of that in the collaboration. Professor Herman Matisse, who is a former graduate from MIT, expert in probability. So basically, this artificial intelligence is very sophisticated, or not always very sophisticated, but rather interpolation of known cases by using some probabilistic method. On the other hand, if you don't have a case that you ever solved in your life, it's not artificial intelligence going to teach you that. So I would say that what is coming in the future is kind of one more competition to worry about, which is artificial intelligence, and that will help to push specialists to be even better specialists than before. So they can provide something that never been done before. Because if you think of that artificial intelligence, you know, if you're owner of the company and you have 10 good guys who are just following my course, and then after that they retire, you lose the knowledge. Unless you have stored what they knew in some kind of computer, and then you choose artificial intelligence to interpolate about the knowledge between Himanshu, Yeshao, Adrian, and so on and so forth. And then you still have their knowledge stored somewhere in the computer. That's actually what artificial intelligence has done. But if you now have to invent something else, like Himanshu bis, or Yeshao bis, or Adrian second, and so on and so forth, unless you have the new guys, you cannot really invent that. So this is just kind of to give you the motivation why you have to learn a little bit more. Hopefully you already have this motivation. Some illustration that we had to deal with. There was a work that we were hired to do after the attack on the World Trade Center in US, where the French army realized they could also have something like a big airplane crashing into the structure they tried to protect. And so happened that this work pushed us into the full analysis of a big commercial plane, where you actually have to understand how it deforms, how to do frictional contact sliding, and so on and so forth, how to fall apart. And this is just defining the loading on the structure that you're trying to protect. Most of the results are confidential. I don't show you anything else other than this picture All the rest was sold for a decent amount. So then you can have like a numerical simulation where you do testing. You can ask, why the hell do I do numerical simulation when I do testing? Because these tests are really incomplete in the sense that first you have to imagine the kind of model that you're trying to build, and then you're using the particular testing in order to have this model fully identified. And then you can do the test on a very fine scale. These are this nano-indentation test. We're testing the properties of a composite material by sticking the needle into this material. This is the kind of machine that allows you to do that. And then you can take like elastic response with the unloading and so on and so forth, all the way to something like a shaking table test where you try to put preferably the real size structure, but often you cannot do that. And then you're trying to simulate the earthquake by moving the table on which the structure is placed, and then basically getting all the observation you can possibly get and identify the behavior for this type of structure. Then, if you're multiphysics, the works that you are involved with, you can have like a fire resistance. This is one for the composite material, the other one is for the masonry. Basically, the idea was that you have to optimize the type of structure so that it can stay for 6 hours before collapsing. 6 hours, for some reason, was deemed to be necessary for fire brigade to come and put down the fire. So basically, the idea was that we had to do many simulations of this fire resistance type of scenario with the variability of the fire and so on and so forth, in order to get a full understanding on what is going on in terms of behavior. So if you get the result that the structure collapsed much before 6 hours, of course, it's not good. If it lasts much longer, again, it's not good because it's not optimized. So basically, if you optimize it, then you can still do the test to kind of test your stuff. But this was done for one of these center technique, these guys helping industry. We had in charge to do like a fire resistant type of tests, which are very costly and consuming, quite dangerous because you can put fire in your environment. So basically, that has to be done under strict control. So if we really talk about going beyond elastic behavior, then you go to so-called nonlinear analysis, nonlinear mechanics. There are really a number of the difficulties to master. First, really like a solid physical basis. In other words, when you do these tests on structures, multi-physics model, multi-scale model, we do not really fully master what is going on. So one has to really kind of build the theory behind it and try to fit the experiments with the theory. So in order to both consolidate theory and consolidate the experiment. Then when you do that, it turns out that many problems of practical interest to engineers, they require huge computational cost. So even at present time, when we have very powerful computers, solution methods, computational tools, and so on, software are still of present interest. Recently, I was in a conference called Uncertainty Computation. And the guys from Japan who are working for a university, they use the models with the billions of degrees of freedom. But then, you know, the fact that you're using billions of degrees of freedom doesn't mean necessarily that you have the most, let's say, pertinent model. Still, they have a big computer, so they use them. But then again, you know, you have to be able to master such a huge amount of information and so on. Then one has to worry about robustness in numerical model. What I mean by robustness, there's something called phenomena like locking. In other words, inability of your finite element approximation to represent what is really going on. You have to have like error estimate to see how much you're wrong. You have parameter identification to see how these parameters are credible, model activity to change the mesh, to prove the results, and so on and so forth. So even if you limit yourself to linear analysis, there's still problems which have not been solved. Basically, something like a shell analysis. This is like a structure which has a very different stiffness in the bending and in the membrane, and it has a quite big sensitivity. Depends on what kind of a deformation mode is triggered. So you can have a very, very big difficulty solving such a problem if you have a shelf. And then finally, the database is always a problem, how to handle pre and post-processing, computer-aided design, and so on and so forth. So I have already seen that many codes which are very good in building the models, but they have lousy, what you call it, pre and post-processing. They are not really much appreciated by the profession. On the other hand, codes which only have excellent pre and post processing, but the models are really kind of Mickey Mouse. They are really highly used because it's so easy to prepare the model. So people just go for the easy life. If you really want to do, like I said, one of the most important motivations to build your theoretical knowledge. So if you want to kind of do deeper studies, here I gave you a number of books, and you can consult the reference list in my book. So first of all, ingredient is, of course, finite element method. So the books which are worldwide known are Zinkesh Taylor. Zinkesh was Professor at Swansea at UK. Taylor is still Professor of Graduate School at UC Berkeley. This year is celebrating 90 years, and we just finished the paper for him. And then you also have people like Jürgen Barth, Tom Hughes, Ted Belichko, who are professor at MIT, Stanford, and Northwestern, who wrote their book. In France, if you really want to have French literature, all my former colleagues like Gouridat, Gilbert Touza, Jean-Louis Batos, who were at UT Compiègne, they wrote the books in French in 90s, but what the hell, still pertinent. Then, as I already mentioned, the book on mechanics, you have a book of Trussell and Knoll. And then after that, my favorite books are Morton Gurton and Ogden. They are kind of mathematical, but still good enough. Then Marsden Hughes is overly mathematical, so you don't understand anything, but just to see how complicated it could be when you go to manifolds, that means curvilinear coordinate system. Then a book of Lubner and plasticity is a really good book to be recommended. And Antman is one in instabilities and so on and so forth. In France, these books are Jean Lemaitre, Jean-Louis Chaboch, and Pierre Ledrez, my former colleagues from Ines Cacham, in the book in French that I had in 2006. Now, in applied mathematics, it's not really books about mathematics that you need. You just need certain notion that engineers need. So really good book is an Gilles Bestin book, who was the advisor of my colleague Herman Matisse. And then Lundberg was professor at Stanford, Golob as well. Parlet was my professor at Berkeley, is arguing the problem. In France, these are Jacques-Louis Lyons, Philippe Serlet, who wrote all the books on mathematics you need. And then finally, functional analysis is about error estimate. So the book in France on that is Brézis from University Pierre Marie Curie or now Sorbonne. And then in English, you have Orden Dankovic and so on and so forth. So the course objective is really to give you the theoretical basis, variational formulation, nonlinear mechanical structures, and explain all sources of nonlinearities as we go along. So then to give you also detailed aspects of the finite element method, and then revisit some of the ideas that come from applied mathematics, matrix computation, stuff like that. Our goal is not only to indicate the problem, but also to understand what exactly is the difficulty and to learn how to solve this problem. So this is really the kind of thing that we are seeking. So let me start with the simplest possible problem that you can imagine. So you take a pen, which is pictured here on the left, and you put it in the, let's say you put it vertically down, just like that, and basically say, okay, this pen is only in the gravity field. That is really the only loading in that pen is a dead load. And I can then imagine if I want to cut a part of this pen and still keep it in the same position, I'll have to put the stress. So basically, the stress is a ratio between the force at the cross section. And basically, I can say that if the pen is homogeneous and so on and so forth, in transverse direction at least, it's a good hypothesis that the stress field is uniform. So if I now choose a coordinate system in a way that x-axis is along the axis of the pen, I can reduce this problem to 1D problem, where the only thing I worry about is a single fiber of this pen. And if I solve this fiber, I can then have solution to all the other fibers. It will be exactly the same. So basically, I can say that either take out the fiber or take, for simplicity, the cross-section is equal to 1, and then I'll scale it to the cross-section at the end. So if I want to define a boundary problem mechanics, what exactly is boundary problem? I take this pen to be part of some more complex structure, and I basically take it out to look at the pen only. And then I have to define the kind of external loading that is applied to this pen. So here it was a gravity field. So it's just mass times gravity acceleration, that's it. And it's like uniform constant loading. Then I have to define behavior. It could be linear elastic, in which case I need Young's modulus, that is the ratio between the stress and the strain. Or it could be nonlinear elastic, in which case I need like a a function which describes how to compute sigma given epsilon. And then I have to define geometry of this pen. In other words, cross-section, I already said, is unit, and the length of the pen is L. So the goal of the problem is to find always the same thing, three fields. Fields, that means the function that goes from 0, one end of the pen, to L, the other end of the pen. That is the displacement. In other words, when I'm sitting in the initial configuration, I displace every point, and I can describe it by a function which is u of x. For every x, I have a displacement u of x. Then if the displacement happen not to be uniform, I have deformation. So the displacement is changing. The quantifying deformation will be epsilon of x. And then finally, the strain or deformation is producing the stresses, sigma of x. So the goal of each and every problem that I'm solving is get displacement, strain, and stresses. And I'm fine. So how do I compute that? Well, for three fields, u epsilon sigma, I need three equations. First equation, kinematics, giving me ratio between displacement and strain. Second, constitutive behavior, giving me what happens between displacement, the deformation and the stresses. And the final one is equilibrium, what happens between the internal forces of stress and external forces, f of x. And then basically, I have to match these fields with a given boundary condition. In other words, so that the displacement at the left boundary corresponds to the displacement I impose, and the stress on the right boundary corresponds to the traction I impose. So basically, if I have linear elasticity, very quickly I write this equation: epsilon is du dx, sigma z times epsilon x, and d sigma dx plus f is equal to 0. And then I can solve the problem. I only impose a traction t on the right-hand side, and very easily compute that I have to have a response which is t bar is equal to E over L times U of L. U of L is the displacement of the free end. E is the imposed traction, E is Young's modulus, L is the length. If I had a cross-section A different than 1, I would have EA rather than just E. So this is a linear problem. What I mean by that, if I impose the value of the force T1, I'm going to produce the displacement which is called U1. If I multiply this force by 2, that is 2 times T1, I'm going to have like a displacement which is 2 times U1. As simple as that. So I can compute this value only for a reference value, and then move it on to the higher kind of level and get it, just scaling it up and down. Now, if I have a nonlinear mechanics, this proportionality is no longer be valid. How that can happen? Well, first of all, I could have something like a nonlinear elasticity, in which case stress is not just product between Young's modulus E and strain, but could be some kind of more complicated function. Here, there's one example: sigma is equal E times epsilon minus epsilon to the power 3. It means that you have like a nonlinear function. You have like a linear part minus this cubic part, and that's the final part. So this actually corresponds to behavior of some kind of cement-based composite materials quite well. And basically, in this present case, when you compute your this kind of imposed traction displacement, you're not going to have a linear function. That means you no longer can simply compute for the reference value, but you have to compute for the real value of your applied loading. Even more interesting is something called inelasticity. Now, one example would be plasticity. Initially, it looks a little bit like a nonlinear elasticity, other than first part being linear, until you go to limit elasticity and then go into this nonlinear hardening. But the difference you see here, in the previous graph, if I go up and I go down, I follow the same path, which is red curve here, and I come to 0. In this case, I follow a red path to go up, that is elastic loading, plastic loading, and then elastic unloading would be like this. So unloading fully, that is reducing this force to 0, you'll never get the back to the original length of your structure. You're going to have residual deformation, so-called plastic deformation, like size, a hardening variable, and so on and so forth. Also, if you look into the results of the typical test for a steel bar that you are putting in a testing machine, these are simple tension tests. You have something like that. This is a thin line is a initial configuration. A thick line is this deformed configuration. So you can see there's the area, the cross-section of the bar is no longer constant. Typically, this leads to something called necking phenomena, where the cross-section of the bar is heavily reduced. And so basically, this indicates that 1D model of plasticity is not fully credible, because you can never capture this change of the cross-section or necking phenomena by simply using 1D model. well, whatever, many people use it because it's the way to start. Now, if you have a large deformation, large displacement, again, you have nonlinearity, but the main source of nonlinearity is the measure of deformation. So up to now, with like a small strain, we could simply have epsilon to be du dx, which is this type of equation. If you now have a large strain, you can no longer afford that. One of the possibilities to take stretch. Stretch is a ratio between initial, the deformed length and initial length. So if you stretch something 2 times, you say stretch is 2. That means deformed length is 2 times as big as the initial length. And then you can take a natural logarithm of your stretch to be like a measure of deformation. And this is just one of the measures. We'll see many of them as we go along. So this is so-called natural strain. And if you take a rubber, for example, you can stretch it without any problem 2 times, 3 times, and so on and so forth. And you can see that the behavior becomes something like that. Initially, it is like a kind of softening, but after it hardens again a lot. And you can also see that this is the form configuration, the thick line, and the thin line is the initial configuration. That these two guys are really not the same in the sense that basically that is a again change of the cross section. Typically, rubber is something like a quasi-incompressible material. In other words, the area of this initial configuration, the area of this form configuration have to be the same. And so you really have to incorporate this into your constitutive behavior. So here's one example for so-called Ogden's material that really fits well the behavior of rubber. So finally, when you have a nonlinear kinematics, you also have nonlinear equilibrium. In other words, you can no longer pretend that the stresses are obtained on the initial configuration as we go along. We'll see that we do. And basically, you have to kind of take into account that to choose the stress. The real stress that X is a so-called Cauchy stress, but this is not very handy to compute because Cauchy stress acts in the deformed configuration, which you don't know. So you have too many unknowns. You have a stress which you don't know, and the deformed configuration you don't know. So that way you can take something like a representation of the Cauchy stress, which could be first Pila Kirchhoff, second Pila Kirchhoff, and so on and so forth. We'll take that as we go. Then finally, if you have like sources of nonlinearity to be pertinent to the boundary condition, which are variable, is a very simple example. We have an elastic bar, which is stretched by this imposed fraction t. I go back to a small displacement setting. There's no problem there. But at a certain point, at the distance g, which is a gap, you put an obstacle. An obstacle could be rigid, but then it's a problem. So in order to replace this rigid obstacle by something you can easily compute, you put a very strong spring K. And so until the displacement UL reaches the value G, it's only the bar which is actually acting. So you're going back to the linear elastic analysis where the slope is E or L. It's up to here. But after that, you come to G, then both the spring of this replacing the obstacle and the stiffness of the bar are acting. And then you have again linear analysis, but a different slope. So strictly speaking, again, this is not a linear problem because if your T1 is here and 2 times T1 there, the displacement U1 and this U2 will not be 2 times U1, simply because you have different slopes in one and the other part. So basically, that's actually what we're going to study in detail, and I'll start with the 1D version, and starting there with a theoretical formulation of problem, introducing strong form, weak form, and variational form in 1D. So let me go into that. I'll take again this bar, let's say a pen, and turn it into a 1D model where cross-section A is equal to 1 by taking hypothesis that the loading is applied in such a way that the stress field is uniform in the cross-section. And I can study simultaneously 2 cases. I can study linear elasticity, where the stress-strain diagram is a straight line, which is defined by Young's modulus here as a slope. Or I can study this nonlinear elasticity, where the behavior is sigma is a function of epsilon. So given epsilon, I can get the corresponding value of sigma, but for each value of epsilon, I get different value of sigma because those are not the same. It could have been this E times epsilon minus epsilon to the power 3, okay? So basically, domain of the bar for me is an open set between 0 and L. And then you have a boundary, which is 2 points at the end for x equal to 0 and x equal to L. So domain omega and the boundary gamma or partial omega together are called omega bar, which is like a closed set. So what we really require to have a well-defined problem is that the boundary where we impose displacement and the boundary where we impose the stresses are not the same boundary. That's what it says here. Gamma u intersection gamma sigma is empty set. And also gamma u and gamma sigma union will be all gamma. Basically, so the idea is that, let's say here gamma u is on the left-hand side, we impose displacement u bar, and gamma sigma is on the right-hand side, we impose the traction T bar on the right-hand side. So we then apply external loading, B of x, and then a boundary condition U bar and T bar. So these are all the loading that are applied to the structure that we have to define. We have to define also geometric characteristic. This is the length of the bar and cross-section A. And finally, the constitutive model or mechanical characteristic, that is Young's modulus if it's linear elastic, and sigma hat or epsilon is like a function of epsilon as if it's non-linear elastic. And then we have to now obtain displacement field U of x, deformation field epsilon x, and stress field sigma x, all the values of x from 0 to L. So how do we go? We have three fields, three equations. So first equation is kinematics. If we have so-called constant displacement field or rigid body motion, so I have this pen and I'm moving it in front of your eyes. Basically, all the points on the pen are moving in the same manner. So U of x is constant. So there is no deformation. I did not deform this pen at all. Now I'm not strong enough to deform. I don't want to break a pen. It's useful. But you have to have something which displacement field varies in x. So then I can use value of U of x and get adjacent value, which is U of x plus dx, where dx is a very small number, 10 to the minus 5. And then take a Taylor's formula to express U of x plus dx as U of x plus the first derivative U of x dx times dx plus 1/2 second derivative for U x dx times dx squared plus all the terms which are of the higher order of dx squared. So this is 10 to the minus 5, then 10 to the minus 10, 10 to the minus 15, so you neglect it. Typically, we will neglect the second order derivative. We say, okay, this is not of interest to us unless we have something called second gradient theory and no local theory, which is not the case here. And we are happy just to define du dx as the difference between u of x plus dx minus u of x divided by x. And that happened to be just derivative of du dx, which is basically defined as infinitesimal strain. When we say infinitesimal strain, that means du dx is much, much smaller than 1. If you take a reasonable steel, it has a 400 megapascal yield stress. That means at the level where the steel starts yielding, the stress is equal to 400 megapascal. Young's modulus of steel is 200,000 megapascal. So if you divide 400 by 200,000, you have 4 by 2 is 2, and then 10 to the minus 3. That means strain is 0.002. This is such a small value that you don't see it at naked eye. And your steel material is already yielding. So for many applications, this small strain theory is quite reasonable, in fact. But there are many other applications where that's not the case. For the moment, we'll stick with this when the infinitesimal strain is just fine. And we can carry on that this has happened to be a definition of our kinematics. So in summary, if I want to compute from the given displacement field U of x, the strain, I simply take the derivative of this displacement field with respect to x, and I get my infinitesimal strain. That's the end of the story. In 1D, there's nothing else. As we go to 3D, we'll see there's, but for the moment, not. Now, since the strain is very small, I just said 400 megapascal divided by 200,000 for Young's modulus is 10 to the minus 3. Basically, you can then say that the form configuration is practically the same as the initial configuration. For any time you need to compute the derivative with respect to the coordinates in the form configuration, you can, without any mistake or very small mistake, get the coordinates in the initial configuration. Or when you have to integrate over the form configuration, you can, without major mistake, integrate over the initial configuration. That simplifies problem a lot when you start further, because then you don't have to worry about different configuration. You can still use initial configuration for all the rest of development. In particular, the rest would be equilibrium equation. So you take a piece of this structure, that's a small piece between x and x plus dx. You cut it out, you isolate it. On one side, you put the stress sigma of x. On the other side, you put the stress sigma of x plus dx multiplied by the cross section, but here cross section is 1, so we drop it. That has to match the external loading which is applied here. So external loading is b of x, it's infinitesimal, so you can take a single value b of x, keep it constant, multiply by dx because it's distributed loading. Then you can use again Taylor's formula to express sigma of x plus dx as a sigma of x plus the first derivative of sigma with respect to x times dx, plus neglecting all the terms of the order which are superior to dx. And then you introduce this value up here. You cancel plus sigma x and minus sigma x, and you are stuck with the d sigma dx plus b equal to 0. In other words, the stresses change according to the applied load b of x. So if b of x varies a certain way, the derivative of sigma has to match this variation in order to keep equilibrium in each and every point x of your structure. These two equations, kinematics, and the hypothesis that these are very small displacement gradients, and equilibrium, d sigma dx plus b, are valid no matter what is behavior of your material. It could be built from whatever you want. It could be solid, it could be fluid, it could be something else. These equations have to match. If you really have a structure built of solid or fluid or whatever it is of your material that you study under hypothesis small displacement gradient theory, these two equations have to match. And then what the different materials will come up with their own personality is when you talk about their constituent equation. Typically, the constituent equation, really, in many type of works, the least understood, the least, let's say, mastered type of thing, in the sense that, in fluids, these two first equations are often related to conservation laws. You conserve momentum, which is another way of writing equilibrium. You conserve energy and so on and so forth. But constituent equation is something that you have to kind of assume and build in order to become fully predicted and validated, of course. So here we'll start with a very simple thing. That is, we have linear elasticity, which means that sigma of x is equal to E of x times epsilon x. E of x will be case when you have a heterogeneous material. In other words, when you, in each and every point of x, Young's modulus might be changing. If you have material which is composite material, it's quite reasonable to assume that. Now, it doesn't really bring much complexity to what you're going to be talking about, other than having additional terms that you just simply handle the same way. So for that reason, the rest of the part, I'll assume that material happen to be homogeneous. In other words, that E is just constant. And then you can handle with this in a simplified way. And then you have nonlinear elasticity. Again, either sigma is a function of epsilon x and x. That means in each and every x, you have a different function. Or if you have a homogeneous material, at each and every x, you have the same function sigma hat, which is characterizing behavior of material. So let me push these things in the same way. Basically, I have now three equations. I have kinematics, epsilon du dx. I have a equilibrium, d sigma dx plus b equal to 0. And I have sigma is equal to E epsilon is one of the illustration. So what I do now, I mix these three equations into a single equation. Namely, I say that, let's say here that kinematics, that epsilon is equal to d dx, and sigma, which is is E times epsilon, can produce something that sigma is equal to E times du dx. Then I put this into the equilibrium equation, which was d sigma dx plus b. And basically, for the linear elasticity, I get something which is E times with the E constant, second derivative of u with respect to x plus b equal to 0. And for the nonlinear case, I get something like a d over dx, sigma tilde of u plus b. Note here that sigma tilde is not the same function as sigma hat for elasticity. It's just like this is often in the nonlinear problem. The biggest confusion is the function, which is the rule, and the value of the function. So one has to be careful enough to not to use the same symbol, which is really the weakness of many books that I read in this case before really figuring what the hell they're talking about. The idea is really like in nonlinear elasticity, I've had the x sigma plus b equal to 0. Here is E times second derivative u plus b. In other words, I need let's look into linear elasticity, which is easier. Of course, you have this boundary condition that displacement at the left-hand boundary has to be equal to u bar, and the traction at the right-hand boundary has to be equal to t bar. That means stress at that place has to be given to a certain value. You can see that this is so-called strong form of the problem. Strong form of the problem is nothing else but the equilibrium equation expressed directly in terms of displacement. So initially, I have only one field to compute. That is the displacement field. And when I compute the displacement field, u of x, by solving this equation, I can go back here, and I can get my strain field, and then I can go back there, and I can get my stress field. And that's the end of the problem. Now, if I want to solve this problem, I can see that the second derivative displacement has to match variation of this b. So if b is in the class of function which we call k minus 2, that means k minus 2 derivatives are continuous. U has to be in the class of function which is ck. In other words, you take two derivatives to match this one. And this puts a lot of constraints in your function. You have certain smoothness, depends on what kind of loading you're applying, and so on and so forth. So solving strong form, in particular in 1D case, is maybe not a problem. You can simply integrate. But in a more general case, solving a strong form could be quite demanding. So rather than that, then people invented the weak form. What do you talk about when you talk about weak form? Well, basically, rather than insisting that all these three equations are verified for each and every point of x, that is equilibrium, constitutive, and kinematics, we say, okay, we'll give up on verification of all these equations. Which one in particular? Well, we verified this equilibrium equation, not in the strong form, not for every x, but we'll just verify that in the weak form, like only for the whole domain omega. In other words, we integrate this weak form over the domain omega, and you say that on the average is the same. In other words, you can put any loading you want on your truss, and then you say, okay, I just sum up all this loading, no matter if it's uniformly distributed or here's bigger, here's smaller, and I give you the reactions which are matching the total which is applied to this load. That's as much as it is. So basically, when you compute your finite element solution, the only thing which is 100% true are reactions. The load that you put in your structure and reactions that you computed from your finite element software these two have to be the same. And if that's not the same, the software is not good. All the rest, there's no match. Basically, because you have weakened the equilibrium equation, so you no longer have a distress. You might have it for certain cases and so on. This is called superconvergence. We'll talk about it in a moment. But in principle, when you're weakening something, that means it's no longer true. Why do we do that? Well, because we'll see this in a moment. When we weaken this type of interpretation, then you don't have to have such a high smoothness of the function that you're trying to use. Because typically what we're going to be using is some kind of polynomials and so on and so forth to represent these functions. So the lower order, the better it is, because high order polynomials tend to have lots of oscillations. So if we now have this weak approach, weak form type approach, basically it is enough to get the solution to be something called Hilbert space. That means these are functions which are square integrable. In other words, if the field u of x, let's say if b is a c minus 1 type of function, then in the strong form, u of x should be a c1 function. That means with a continuous first derivative. Whereas in the weak form, u of x is enough to be h1 function. That means the function for which the function itself and the first derivative are square integrable functions. So they can be discontinuous from one point to another. So basically, the fact that the function is, let's say, square integrable, especially in terms of this first derivative, you can kind of guess behind that du dx is just epsilon. And if I multiply this by e, this will be something like a stress. And then if you multiply strain du dx times e times du dx, you're going to get something like energy. And that basically, you were talking about something where the function that we are using a finite energy function. In other words, if it's real structure, we are just happy to reproduce the solution where the energy is bounded. It's a finite energy type of value. and that will be just fine for computing our solution. So we are doing that simply because we want to be more efficient in computing the solution. We want to make it more robust, more easy. And then again, that enlarges a number of kind of candidates for the true solution in many different ways. The fact that we are using polynomials also is very important, because if the solution to our problem is so-called analytical function, you can always represent this function using this Taylor series development by using polynomials. Basically, because at any point, whatever x bar, you have a f of x bar plus x minus x bar times first derivative plus 1/2 x minus x bar squared times second derivative, and so on and so forth. So intrinsically, you can see that by appealing to these physical notions, in other words, the fact that the solution is an analytical function and that you need a finite energy approximation, you have all the sound basis to be able to compute any problem. In other words, you can always get a solution. Now, how good is your solution? Well, then now it depends on how much effort you put in there. So I would say that's really the big privilege of using these software tools, because no matter what, they really need somebody who is expert enough to get all the details to get an optimal solution. So I don't know whether artificial intelligence will be able to replace these guys doing this, but up to now, you cannot take people cleaning the toilets and working for software company, put them when they finish cleaning the toilet behind the computer and get to produce something good. I don't know whether this is going to change, but hopefully not too much. In other words, you really need much more understanding what is going on to be able to solve this problem. So basically, the key point here is not only that you're averaging, I mean, you can call this your averaging equilibrium equation. Only average is verified by integrating it divided by L, whatever you can call it averaging. But not only that you're averaging, but you're multiplying with a W. In other words, you're putting something called weighting function. So this thing is often called weighting residual. I think in Zinke-Taylor, they call it weighting residual method. In other words, you can take how this equilibrium is not verified by putting the weights and then integrating to see whether the average is correct. Now, these weights have to have the same regularity. They're also square integrable function with their first derivative square integrable. And on top of that, at the place where you put real displacement, u bar, you want to have this weight to be equal to 0. I'll explain that in a moment why. So basically, then the weak form could be written this way. Given your loading and let's say the boundary condition here, I put u bar equal to 0. Basically, you can write that for nonlinear elasticity dw dx, this will be like a strain or deformation computed from the weighting function w dx has to match wb dx. B is external loading times dx is the total loading applied x multiplied by w, and w times t bar at gamma sigma, that is w of L, is equal to 0. In linear elasticity, this is the same, the second part, only here, sigma is in fact equal to E times du dx. So this way, what you're really doing is basically you're comparing the product between the stresses or internal forces with the corresponding strain from this weighting function, and the product between external forces, B and T bar, with corresponding displacements. And you're matching the two. So this gives you the kind of physical justification. In fact, we call this weighting residual, and W is weighting function, but there are some more names for that. I'll come to that in a second. Now, this I'll give you this as a small homework. You can see that, first of all, that d sigma dx plus b will always give you this is the strong form. If you start with that, you multiply by W, multiply by -1, then you integrate by part, and you can get that the weak form matches precisely what we've done here. Now, the inverse is true only if the solution of the weak form is sufficiently regular. In other words, if I start with this, I'm then asking whether this is really true. So basically, I can take this one. Stop share up. And where's my board? So if I So if I take a bar and I have a two node element, okay, and then basically I have let's say I have the interpolation of this. If I have something like the load would be something like a B here. Okay, and here I have here yep. Okay, and here I have a U equal to 0. So if I assume that my displacement field, if my displacement field is something like let me put it this way. If I assume that my displacement field for two node element would be something like up here U of x equal to U1 times 1 minus x over L plus U2 times x over L. I have to show if this verifies. Strong and weak form. Or only one. Okay. So is that clear for the one that you can do like a small homeworks and keep it there for you? Okay. Is that fine? Perfect. So last one, share screen again, up. So basically, what I really want to say here that if you compute the software solution with a very simple problem that you have truss bar type of elements and you get your stress field and so on and so forth, in fact, you really don't have a exact stress field, and you will find that as you go along, and I'll leave you with that to worry about that a little bit later. Now, the notion of this comparison by weighting function and stuff I already said, but sometimes you can call this as instead of the principle of weighted residual, you can call it principle of virtual work. What that means is basically you have your deformed configuration, and then you imagine possible displacement of deformed configuration. You call this displacement virtual displacement. It has exactly the same role as this weighting parameter W. So in other words, virtual displacement has to be equal to 0 when you impose the real displacement. It has to be a square integrable function for the first derivative of the rest of it. And that is simply in truss bar case, again, simply like a horizontal displacement is the only thing that can happen. And then you can say that the principle of virtual displacement says that if the bar is in equilibrium, the work of the internal forces on this virtual displacement is matching the work of the external forces. Now, what is the work of internal forces? Well, this is internal forces are stress is sigma multiplied by the virtual displacement deformation W dx. The W dx is a virtual deformation computed from virtual displacement W. And then work of the external forces is WB. B times dx is the load applied to the particular point, and W is a given type of displacement. And then E bar is applied at the W of L, multiply W L, give you the work of external forces. So matching these two together, you actually get back to something called the principle of virtual work. In other words, principle of virtual work is a very handy method of testing equilibrium. If you take a 3D problem, equilibrium equations are vector equation. You have like three equilibrium of forces, three equations of force equilibrium, then three equations of moment equilibrium. Whereas in virtual work, you can always take a one scale equation at a time and simply put that. And then W is like a tool of imagining certain model. In other words, you don't have to test equilibrium in any particular model. You can test equilibrium for the given model W. And this is basically adjusting the modeling option and doing this something called model reduction, so on and so forth, which is rather fashionable nowadays in some kind of sense. Now, W can also be called the variation. And then basically the last interpretation, we call it weighted residual method, we call it virtual principle of virtual work method, and now it's also called the calculus variation type of approach. And basically the last result is something called the fundamental lemma of calculus variation. In other words, the first variation of some kind of functional is equal to 0. What are we talking about here? First of all, calculus variation is really a wonderful type of domain of applied mathematics. Is probably one that has reached huge success in many applications, and there are many books written about that. What I never really liked, but I still use this nonetheless, is that the notation that many people are using. Until I found the book by Hildebrand is finally the one who really explained to me what the hell is going on. Let me explain this a little bit better. Often they are using this symbol little delta. Delta P would be like a variation of the functional. When you have a normal derivative, you have like a dw dx is just simply normal derivative. You take a small piece of dw, a small piece of dx, and you compare these two, this is called derivative. But if you take this type of delta, it's not so obvious because P is a functional. Functional is a function of a function. So you have a displacement field, which is a function. It goes from 0 to L. For x from 0 to L, you have for every value of x, you have different value of u. And now you want to produce a functional. So you take u of x, and then you produce the total potential energy as a functional, which is internal energy. Internal energy happen to be here quadratic form with linear elasticity. It's 1/2 epsilon times E times epsilon. And then you have external energy, which is minus U times B plus U T bar, and so on and so forth. So basically, the idea is that you are computing a single value, like a value of function. Only the argument is not parameter x, but it's another function u of x. So this is why you have to do variations. Basically, if you really want to do this illustration, let me try to illustrate that a little bit better. If I should have practiced my whiteboard a little bit better. I'm not sure I'm gonna do it so well, but what the hell? If you have a hopefully this will allow me not to write about this one pen. Yeah, pen will be probably good enough. So if I have, this will be like my bar, and this will be like a u bar, and then from that one I have my displacement, which is u of x. So here would be and then from here I can have some variation, which are going up and down, and I have something like that. So this thing here, the kind of straightish line is my u of x, and this one goes up and down. It is my different variation. So I can have a variation that goes like that. I can have a variation that goes like that, and so on and so forth. So I can have many candidates for this variation. And I want to have one which is finally minimizing total potential energy. So let me do how this is finally done. So if I'm basically trying to compute the minimum of total potential energy, this is like computing the minimum function. If I have function f of x, how do I compute minimum? Here's the graph of the function. The minimum is at the point x bar, where the function has the smallest possible value. So basically, first I compute the first derivative and make it sure that it's equal to 0. That gives me this definition of x bar. And then I check if it's really minimum if the second derivative of this guy happens to be positive, because that means that goes up and that goes up as well. So this is indeed minimum. So, okay, for the real function, I know how to do that. But how do I do that for the functional? And that's actually what this explanation by Hildebrand was really nice. Basically, I take all these variations, which is what I was putting on the u of x was a particular displacement that is really the displacement I'm trying to find. I don't know for the moment. In order to find it, I make a variation. So admissible variations are all these w of x. They share the same thing. They are square integrable functions, with the first derivative being square integrable. At value of where I impose the real displacement, they have value 0. And then I can parameterize all these by some kind of parameter small epsilon. Maybe it's a lousy choice. It's not deformation. It's now this var epsilon. So in LaTeX, you have the choice of one epsilon, the other epsilon. So this is simply parameter. So this way I can replace this Fresher derivative I was using before, like dw dx is something like Fresher derivative, with something called Gatto derivative or directional derivative, where I'm computing derivative with respect to some kind of given direction, which is now specified by this variation. So this could be formally written as a p of u plus epsilon w, which is this u with index epsilon, minus p of u divided by epsilon, and then take derivative with respect to epsilon. So it becomes Fresher derivative with respect to this parameter epsilon, and then put epsilon equal to 0, and then you get that. If you go through this procedure for the given total potential energy, where the internal energy is a quadratic form, you will recover precisely the weak form that we had just written. In other words, weak form becomes like the first variation of the total potential energy. It happens to be if the configuration of equilibrium equal to 0. And then second derivative, you take a first derivative of the first derivative again. So what is in the first derivative? In the first derivative, the only place where something that's this becomes w, this becomes w. So the only thing where actually u is hiding still is sigma is equal to e times du dx. So when you now compute the second derivative, this du dx will become dw dx. And basically you can say that the second derivative could be either positive or 0. But if it's 0, that would imply that w of x is a constant. And together with w of gamma u equal to 0, that would imply that the only w which is acceptable is w equal to 0. But then this is nothing. There's no variation. So this one is included. And so the only thing which finally is possible is that you have actually this one to be positive. And so this way you get by the minimum total potential energy, it says that you have a deformed configuration. And then just a small perturbation, a little whatever insect came on top of the structure. It's really like a, almost negligible, but still some perturbation. So you can say that the energy will be like a u that you already had in the deformed configuration plus perturbation by this weight of the insect compared against the energy that you had in the form configuration. This is like first derivative plus 1/2 second derivative and so on and so forth. You can say this energy will always be bigger, given that the first variation is 0 and the second is positive. 1/2 is missing. But basically, the idea is that when this set is gone, that means structure will come back to its own configuration. So three interpretations of this principle: weighted residual, principle of virtual work, and variational principle. The last one is the most powerful in the sense that not only gives you that the first variation of the potential energy is equal to equilibrium, but it's also that second variation being positive means that equilibrium is stable. In other words, after any perturbation, you remove perturbation, the equilibrium will be recovered, and you come back to this deformed configuration. So basically, this is used for many types of applications, including, let's say, solution existence uniqueness. These type of studies are done in the books that I already cited, in functional analysis, Bresis, or the culture, so on and so forth. For example, when you have a composite material and you're building the response of your material by using the, let's say, strain energy type of functional W, functional strain du dx, you want this to be bounded. It means that you have to be continuous, you have to be kind of bounded from above, and then coercive, bounded from below, which is again logical because whatever you're deforming your structure, you cannot be producing infinite energy. Infinite energy does not exist, at least for the moment. So basically, the idea is really like these are mathematical notions, but one should not be too excited about that. It's simply giving the kind of common sense that when you're deforming a material, if it's kind of functioning, you should be in this domain and doing this correctly. So basically, that was the ideas that I wanted to discuss here. And after that, I want to go into these things with the second part that we're going to do, basic solution procedures and so on and so forth. So let me just search here up. I need this to see who are, okay. Imashu, Adrian. Okay. So, do we have any question or comment before we go for a break, or? You hear me well, or everything's fine?
Yes, Professor, we hear you.
Okay, that's good. So perfect. We can stop here for 15 minutes. We start again at 10:30. Okay, guys. Bon café, whatever you're gonna take. Stay healthy, and we'll keep pause recording up.
Professor, we cannot hear you.
Unmute. Yeah, that would be like, okay, now it's okay. You hear me?
Yes, now it's okay.
Okay. So basically, the idea is that you start first with the basic solution procedure, stating how to solve this simple problem, and then keep it a little bit more and more complex in the process. And hopefully, the benefit of doing this in 1D setting, where I can give you a couple of exercises, you can really understand each and every, let's say, step, and really recognize that in much more complicated kind of situation, the same steps are simply repeated. That's all. So what are we trying to do? First of all, we're going to do a solution which is not exact. In other words, rather than looking even for the solution of the weak form, where we actually simplify the kind of function which is suitable. In other words, we are going for a square integrable function with the first derivative to be square integrable, rather than these to be a second type of derivative continuous functions. Definitely there are many more functions which are kind of square integrable than those that are continuous second derivative. But even that is not good enough, because we are really facing a very complicated problem, and we want to be able to solve them all. And basically then we appeal to this type of notion of a solution being analytic function. Analytic function means you can develop the function in the Taylor series development if you reach every point, and intrinsically we're using the polynomial developments. You have to be aware nowadays there are many methods which are not using only polynomials. For example, at a certain point, a very fashionable method was something called isogeometric method, and so on and so forth. They're using nerves. These are rational type of functions, stuff like that, which have very seductive type of appearance when you have geometrically nonlinear response and so on and so forth. But you lose something which is called the partition of unity property. In other words, when you take polynomials, you can represent each and every analytical function by using polynomials. Then the game becomes how many of these polynomials you want to use. When I say how many, you can be like using many for the very small subdomains or very small finite elements. It's called H method. Or you can use this higher order polynomials with something called P method on the larger domains. But whatever choice you make, either H or P, you can get as close as you want to the exact solution. When I say as close as you want, that means you just put many of these elements and many more, and that costs you more money, and that's it. So it's really kind of very honest type of deal. The more work you put, the more quality you get. So the difference is rather small. We have been using some kind of a approximation to our field. That is, here we have a real displacement field U, and we have a virtual displacement field W, or variation or weighting function. And then we put an index H. H is a reminder of discretization. H will be typical length of the subdomain, or typical length of the element. And then you say that inside, the function should be constructed by using some kind of interpolation functions, or often called shape functions. N of x, NA of x is used the same way for U and W, and the only difference is using these unknown parameters. So by using this discrete approximation, that means discretizing in space, we're actually turning the problem to something more simple, where the unknown values are just these parameters UA, and eventually this WA that we can choose arbitrarily. So we can go for something called Galerkin method or something called Witz method. Both methods come to the same result in the framework of elasticity we're discussing here, but they have a different starting point. Galerkin method starts from the weak form, whereas Witz method starts from the potential of the energy. So in the Galerkin method, basically you have the weak form is expressed as a function of UH of x and WH of x to be equal to 0. That gives you the unknown values for your UH. That is simply computing these parameters UA. Whereas in this approximation, we have to minimize the total potential energy, which is now a function of UH, which is again U with the index epsilon, which is again sum of UH and the WH multiplied by epsilon. So this type of thing is has to follow the notion of the square integral function of the first derivative square integral. In other words, the shape functions NA have to inherit this type of property. They have to be square integrable, and the first derivative have to be square integrable. So even simplest choice, I was just writing a moment ago, was a polynomial x over L. So this is definitely square integrable because it's x squared divided by L squared integrated. It's again give you something like L to the power 3 over 3 divided by L squared. That's L over 3. Or if you take derivative, derivative of x over L, derivative is 1 over L. So again, square integrable will give you back your 1 over L and so on and so forth. So the square integrability comes into these shape functions, and the unknown parameters are now becoming the unknown of the problem. These are UA. These are simply the values that you choose. Now, a particular choice of this shape function would allow you to give a physical identification to these parameters. It doesn't have to be so. I mean, initially, when they had Ritz method, that was not necessarily the case, but when we come down to finite element method, that really has become the usual choice. In other words, these parameters UA are nothing but the nodal value of the displacement field at certain nodes. And nodes are let's say how you separate these different subdomains or different finite elements. So basically, when we go for the finite element method, rather than Ritz method and Galerkin method, these functions are chosen globally over the whole domain from 0 to L. In the finite element method, we split this domain into subdomains from, let's say, to XA to XA plus 1, and we focus upon a particular subdomain. In this particular subdomain, we construct a shape function NA of x to be equal to XA plus 1 minus x divided by LE, where LE is a length of this element that goes with XA to XA plus 1. And the second branch is x minus xa minus 1 times Le minus 1, where Le minus 1 is again length of the element that goes from xa minus 1 to xa. Now, the value of this function for x equal to xa is equal to 1. And it's equal to 0 on all the other nodes, what we call. So here's the illustration. When you take a bar that goes from 1 to L, to 0 to L, we split this into a number of elements. We call it n elements. Could be 10, 12, 20, 100, whatever you want to have. And then, as long as many elements you have, each element has 2 nodes. So basically, you go, typically, if you have number of elements, number of nodes would be plus 1, the number of elements, if you have such a simple situation. So your typical shape function would be equal to 1 when the x is equal to a, and 0 on the remaining, on these 2 adjacent nodes and all the other nodes. So basically, this is your shape function a, this is your function na plus 1. And you can see that now you have something called local support. In other words, you're building your field only from the subdomains which actually attach to this particular node. So this really makes your arrays that you're finally going to be using a little bit more sparse, which is quite suitable for the finite element computation to reduce the computational effort. And basically, it still allows you to have as precise result as you want, simply by defining the mesh, for example. Then in the linear elasticity, when you take this choice, you basically take the computation of the derivative. In other words, when you need the strain field, you simply take derivative of the DUH with respect to dx. That amounts to taking the derivative of NAX with respect to x, gives you obviously the constant values in each subdomain, multiplied by these coefficients. You multiply this by Young's modulus, you get the stress. So the final result is actually written here. My equation that was a weak form of the equilibrium equation, characterizing either linear elasticity or nonlinear elasticity, we first start with linear, will amount to this, which is basically something called Galerkin equation that is expressing the weak form equilibrium equation in terms of the chosen shape functions. Now you can see that this could be written as a sum over all nodes. You see here one node to all the way to the final one. The product between the let's say the parameters for the virtual displacement field which is WA, times the residual. And the residual happened to be a product between the stiffness matrix, derivative of dA dx times E times dB dx, integrated over the length of the element, dx, and basically multiplied by the unknown parameters that you use to construct the real displacement field, equal to F external at the nodal value A, which is again integral of the shape function and the distributed loading B, plus NAX times T bar. So this is the kind of function that we call Galerkin equation. So this is the kind of result that we call Galerkin equation, which simply expresses the, let's say, the final product of the finite element discretization, which is the weak form of the equilibrium equation in terms of the chosen shape functions. So basically, then you can say at the first node, WA has to be equal to 0, because this is the node where you know the real displacement. You put a support, and all the others are unknown. So A can really go from 2 to all the way to the end. And basically, I can then say that this residual for the arbitrary WA for all the nodes from 2 to n of nodes can be chosen the arbitrary value. So residual then has to be equal to 0. Hence, as the final product of my procedure here, I recover a set of the equilibrium equation, which are expressed as a stiffness matrix under the nodal displacement equal to the equivalent nodal loads. That simply imposes that each and every residual for every node is equal to 0. That's why you called it weighted residual. You can see the stiffness matrix is characterizing only the structure. You have your geometric property, this is the length of the structure, and your material property, this Young's modulus. Eventually, cross-section would be sticking here if you had something different than 1, and the given shape functions. This is how you construct the stiffness matrix in the terms of your model that you imagine. It can be truss bar, it could be beam, shell, solid, and so on and so forth. Now, external load vector is not really a load. This is really the work on the external forces on the given weighting function or given virtual displacement or given variations. Basically, and in that sense, it's really like a comparison again of the work of the internal forces versus work of the internal forces by the fact that we kick out the virtual displacement nodal parameters, which are nodal displacement virtual field. We actually recover something which has the dimension of the forces. But in reality, these forces are sort of equivalent forces that are expressing the work of those forces. So one really has to keep in mind what we're doing here. So after that, the final product of discretization by the finite element is a set of linear algebraic equations. K, stiffness matrix, times U, unknown nodal displacement, equal to F external, which are a set of the external, let's say, equivalent loads. So basically, the next step is how to solve set of algebraic linear equations. This is something which has kept mathematics community for a long time very busy, and even in the present time, we still don't have a perfect method to do that. You have many iterative methods. You also have a direct method, the one that I want to discuss here, and I'll come back to that in a moment. But let me just comment on that, given that I know how to solve this set equation. In other words, for known value of the stiffness matrix, that as components are computed from the material properties, geometric properties, and chosen shape functions, I can compute each every component of KAB. For the given value of loading and the given shape function and geometric property, I can compute each and every component of FA. So I know K, I know F, I'm computing U. Theory, I can simply say U is equal K minus 1 times F, where K minus 1 is inverse of this matrix K. Of course, this is the least efficient way of computing. And you can do that only for a very simple problem, like a couple of equations, stuff like that. More frequently, you're doing that in a smarter way. So once you computed your nodal displacement, you can go back and you can recover displacement U for each and every point by using your interpolation. And then you can also complete the full solution by computing your strain, simply by computing the derivative of the computed displacement field, which amounts to saying multiplying this computed value of the nodal displacement with a B, and B is the derivative of your shape function. So you have like minus 1 over LE or plus 1 over LE, depends on where you are in this particular field. But that amounts basically to taking in the two-node truss bar element, two displacement at the end of the bar, UA plus 1 minus UA divided by LE. Then I compute the stress simply by multiplying this by Young's modulus, and that's the end of the story. So if I have a nonlinear computation, that's going to be repeated in a systematic way, but only in something that we call incremental analysis. I'll get back in a second. So for example, if you have that, like here, this will be, again, the same approximation for my real displacement field, my same approximation for the virtual displacement field. This will give me internal force as a function of the strain field, which is computed, as we just mentioned, B times UA. So this is your B times U. And a function of that will be giving internal forces. So this basically taking the stress, multiply by the derivative of the shear function for a particular node, and you get your internal force. Contrary to linear elasticity, you don't get a linear connection like this stiffness matrix times U, but you get some kind of nonlinear expression. And external forces, on the other hand, are exactly the same. Whether it's linear or nonlinear, external forces are just simply that, because the constitutive behavior doesn't have to do nothing with external forces. So basically now you have a set of nonlinear algebraic equations. You have to solve this. And these are actually two things that I wanted to address as the first part of the solution procedure. So basically this will be done in the framework of incremental analysis. We'll see you just recycle what you learned for a linear analysis and you keep repeating it increment after increment. Just to illustrate, let me take a very simple problem, which you also have in the book. Here you have a single bar. It has a uniform loading B. So B of x is constant, is equal to the value B, given value. Then we have imposed displacement U bar, and then you have imposed traction T bar. I'm trying to compute sigma linear analysis when E times epsilon. I'm computing also the simple model like to be a quadratic behavior with respect to epsilon. So sigma is equal to E times epsilon plus sine of epsilon times epsilon squared. So basically you will have a, let's say, a linear elasticity solution. So basically I'm mixing these three equations. This is kinematics, cos theta equation, equilibrium. I stick kinematics into a cos theta equation. I get sigma to be equal to E times du dx. I put this back into the equation of equilibrium. I get this E times second derivative U plus B equal to 0. Obviously, this is second order differential equation, which needs to be integrated 2 times. I need 2 boundary conditions. That's really the role of this boundary condition. One is displacement goes to be known U bar, and the other one is stress at the free end to be known equal to T bar. So I integrate once. I get my derivative du dx to be equal to minus BE, the OE times x plus C1. So by taking this condition that the free end, my stress is equal to T bar, I can get the C1 is equal to T bar plus BL divided by E. And then I stick it back here, and this is the expression for my first derivative of strain field computed from strain form. This is exact strain field for each and every value of x in this deformed bar. Then I multiply this by Young's modulus, and from strain field, I get my stress field. So it amounts to say that sigma of x equal to T bar minus plus BL minus x. But you can get that directly from your bar if you take it at certain distance x, and you take all the load on the left-hand side to be represented by the sigma, and on the right-hand side will be T bar plus B times L minus x, and these two have to match. No matter what's the situation, these two have to match. So from this one, if I integrate once more and I use this boundary condition, I can get U bar plus Tx divided by E plus Bx squared to E. Here's a small homework. You can check if this is right. I might not be right. And then U of L is equal to U bar plus T bar L divided by E plus BL squared divided by 2E. So this is the solution of your exact formulation or strong formulation where you have a displacement U bar equal to left-hand side and U of L on the right-hand side. Now let's see when you go to the weak form. If I take the simplest approximation, that is a linear approximation of my two elements, or my two node truss bar element, and I have this W to be W1 times 1 minus X over L and W2 times X over L, UH is equal to U1 times 1 minus X over L and U2 X over L. Then I impose my displacement U bar on this interpolation because I know on the left-hand side displacement has to be equal to U bar, and I impose the W1 has to be equal to 0 because that actually makes the things kinematically admissible for the virtual displacement. So this has been imposed, so my interpolation for W becomes that. So the Galerkin equation, that is the weak form of the equilibrium equation, with the given approximation I just solution with the linear polynomial for a single bar would amount to that. This would be part where you actually get the stiffness metric computation, and then is the contribution of the applied loading T bar B and applied displacement U bar. So you can get the contribution for the component of K22 is simply equal to the derivative of function N2 times E times the derivative of function N2. So when you integrate this, it becomes simply E over L. And F2, you have contribution from the distributed load, from the traction, and from the pose displacement. So basically, you get at the end that U2 is equal to U bar plus T bar L divided by E, BL squared divided by 2E, which is precisely the same thing as the one that we had in the strong form. So these two results are the same, even though the strong form required quadratic polynomials and weak form has only linear polynomials. They still have these displacements to match at the nodal points. This is some result that is called the superconvergence type of thing. In 1D case, the results of the nodal displacement are exact at the nodes, which is really like unique feature for this strong form type of solution. So basically, once you have your displacement and you have a strong form that is matching this, you can also check that the strain that's the derivative of this weak form type of solution will amount to T bar plus BL over 2. And basically, sigma H will be T bar plus BL over 2. It turns out that these two things are also the same, but at the middle of the elements. So again, you have the kind of thing that the strong form and weak form in 1D problem for the linear elasticity precisely give the same results, only at the nodes in terms of displacement points, and they get the strain and stresses in the center of each element. So it happened to be the center of each element is something called the integration points for 1D case. We'll see. We'll come back in a minute during this lecture today, and basically this would actually give you the best value of the field that you can compute. So this is really a very big result in the sense that you can obtain a superior results which are equally good as the strong form, but only at particular points. So really one has to know what one is doing. And these points are called so-called Barlow points because Barlow was the guy who wrote the first paper on this. And turns out that when you have these error estimates, so there's something called goal-oriented error estimates, that you want to obtain the best results for the derivative of du dx, that means the strain field integrated from 0 to L, that amounts to saying I need the best value for displacement of UL and displacement U0. It turns out there's a finite element solution does not make any mistake there. And that really confirms your superconvergence property. In fact, among all the discretization method, if you talk about statics, the finite element method is the method which delivers the best result in the so-called energy norm. So if you really want to have like a energy norm would be, you have a difference between your true solution, the approximate solution, put into the functional where you compute energy, that is you compute first derivative, you put in squared, you multiply 1.5 and so on and so forth. And you cannot get better result than by the finite element method. So all the problem like linear elasticity or even non-linear elasticity with potential or stationary heat transfer, so on and so forth, the best discretization method is by far the finite element method. And then you have many other methods. Of course, if you have dynamics, we'll talk about that as well. Then you have to have some kind of other type of methods where one has to really worry about how to construct all this. So this was about linear elasticity. If I have now nonlinear elasticity, you have solution to the strong form. Again, I'm mixing these three equations. This is kinematics. This is equilibrium equation. It happened to be the same like in the previous case. We said whatever is constitutive behavior, these two do not change. And then you have a constitutive behavior to be different than the linear elasticity by adding this quadratic term epsilon squared multiplied by sine epsilon. So this way you can climb in positive and you can subtract in negative part. So this is now your equilibrium equation with two boundary conditions. I can then integrate it, but it's kind of much tougher to integrate because basically now it's like a nonlinear equation. So when I'm integrated once, I recover this. Basically, the sigma is equal to T bar plus B L minus X, which is okay because basically I'm still just comparing the equilibrium. And so it happens that stress is now computed by a more complicated way, but with this nonlinear constitutive equation of nonlinear elasticity, but still it has to verify equilibrium, which says that sigma at x, any point x, is equal simply to whatever is left to the free end, which is p bar plus b times L minus x, and nothing is more than that. Now, if I want to integrate a second time, this becomes a little bit trickier. I never really managed to put enough energy to integrate it, and I didn't do it to have a strong form solution. So if you know how to do it, so much better. Take this like for the homework. Another homework could be if you think about this to be negative sign. In other words, I have like this to be positive and this to be negative. I can actually challenge you to have this as a little let's say homework. In other words, if I have this, where's my stuff? Not new share. I want stop share, and I want this whiteboard. Okay. So if I have this one to be if this is my behavior, so this has to be done with a sigma equal to E times epsilon minus sine on epsilon times epsilon squared. Solve the solve problem like I'm going to present to you as I started here right now. Okay, so let's go to that, and basically how we can solve it. In the weak form, this nonlinear elasticity problem I can solve more easily. I take the same interpolation for W and UH, just as before, the simple linear polynomials for two node trust bar element, with the chain function being 1 minus x over L and x over L. Please note the first one has unit value on the left-hand side, 0 on the other side, and the second one has 0 on the left-hand side and 1 on the right-hand side. So again, I introduced that I know the displacement, real displacement on the left-hand side, which is U bar, and I know that kinematic adaptability imposes W1 has to be equal to 0. And so when I go through this procedure, I recover this time around a nonlinear algebraic equation with the unknown value, which is U2, which is unknown displacement at the free end. So it so happens that this is quadratic equation, and I can assume that T being positive and B being positive, the bar is stretched. In other words, even if I impose displacement U bar, on the right-hand side, because I'm stretching the bar, U2 will be bigger than the displacement U bar. So I can simply take the sign to be +1, and then basically remove this one, and I recover a quadratic equation in unknown value of displacement U2. That's the reason I took it to be, let's say, this way, because it's one of the few equations I know how to solve by heart. This is ax squared plus bx plus c equal to 0. You know, the x12 is equal to minus b plus 1. This will be squared minus 4ac divided by 2a. And basically, this actually this result. You take a positive value only, and you get U bar to be equal LO2 multiplied by 1 plus 4 T bar plus B LO2 divided by E, or the square under square root minus 1. And so basically, this is just one of the few problems I can solve this directly without any problem, because it's a single equation with the quadratic form, and it all fits well. In many other cases, when I have nonlinear elasticity, there's no way I can solve that. Already strong form I could not solve even here. And then weak form, I could solve that under certain hypothesis, but I need a more general solution for that. So let me go back to this more general solution. So this was just illustrative example, and I give you this couple of, let's say, motivational homeworks to do that and try to a little bit play with that and do it better. But if you have a much larger system, because this is the main interest of using such an approximation method, to be able to solve problem in a way which is credible to engineers, that means you really have to put lots of these elements, and you compute K equal to Ku equal to F. So you know the stiffness matrix K, you know external load vector F, and you're looking for the nodal displacement U. So as I said, there are many iterative methods. There's a Jacobi method, Gauss-Seidel method, and so on and so forth, conjugate gradient method, and so on. Basically, you're trying to do this iteratively. And then among all those methods, something called Gedrecht method, which was invented by Gauss. And basically, this method has really many nice features, in a sense that gives you kind of the most efficient solution, and also give you the estimate of when the things can go wrong and how they can go wrong. Let me elaborate on that a little bit. Namely, the Gauss method follows the three phases of the solving the algebraic set of equations. First phase is you take a stiffness matrix and you factorize it as the product between uppercase L and uppercase U. There's an error here, it should have been uppercase U, okay? So basically, this thing, L, is a lower triangular matrix. In other words, it has this form, which is one components at the main diagonal, and all the other components underneath are non-zero, whereas all the components above are zero. And then U is upper triangular matrix, which has all the components on the main diagonal and above to be non-zero, and all the components underneath to be equal to zero. It turns out you can always write K as the product of these two, given the symmetry of K and so on and so forth. And basically, once you've done that, then you take a K to be product of LU, which is taken here. You have little u to be unknowns and F. So the first one you call product between uppercase U, which is this matrix, and unknown values in order space of little u to be some kind of unknown vector Y. And then you're solving the system L, this matrix here, times unknown vector Y equal to F external. Now, you know F external, you know L because you just factorize K, and you don't know Y. This process is called forward reduction. Why? Because you'll see this in a moment. I start with the first equation, there's only one unknown, then I go immediately to the second, using this value that I compute from the first. Again, there's an unknown and so on and so forth. So I go from top to the bottom in the forward reduction. I'm reducing the number of unknowns by one in each and every of those equations I visit. Once I computed Y, now it's known. So now I know that uppercase U times unknown values of model space of lowercase u equal to Y, which I just computed. And now I can start with the last equation. I compute the last value of U, and then going back, so-called backward substitution to the first value of U. And this is like three steps. You have like a triangle decomposition, forward reduction, back substitution, and you solve the problem. So basically, these three steps obviously are not the same cost. First of all, the most costly is the decomposition. If you have n equation, that means like, I don't know, 10 to the power 3, 1,000 equations, the cost of factorizing the matrix will be n to the power 3. That means 10 to the power 9. You are in the billions, a number of operations. Of course, multiply 2/3 if you have it, and so on. Now, and if you have forward reduction, back substitution, your order of magnitude faster. In other words, you are at the millions. You are 10 to the power 6 if you have 10 to the power 3 equations. So that's the first point. The most costly, the one that you really have to take care of, is the triangle decomposition. And that's why there's a special, let's say, numbering and schemes and so on and so forth to reduce the cost of this. Then you have something called the band representation of the stiffness matrix, which is typical for this one-dimensional problem, because the adjacent element only see, let's say, each other. They don't see the other. So you have like a three-diagonal type of form, so it becomes much faster to compute. Or you have something called skyline and so on and so forth. There's really, once I took a whole course about this sparse matrix computation that come from very different applications. We have like these books and the methods that are developed for solving this huge, let's say, system of equation with the sparse matrices and so on and so forth to reduce the computational cost. No matter how big is the computer, there's always interest to use the best possible method, and then you have whatever this numbering scheme to reduce the cost. So good software has this automatically where you can reduce number of equations, because the worst thing you can do is like you have the least efficient type of solution scheme. You're waiting for zillions of years to solve your problem. Especially tomorrow morning, you have to give a report to your boss. So what the hell? If you have no result, you're really in big trouble. So basically, the second point that is interesting how to compute even more efficiently is, as I said, is like if you have symmetry, then you can store this as U is just like a product of D and L transpose. Where the L transpose is transpose of L, and D is diagonal matrix, which just these diagonal term D1 to the until the n. So this can actually further divide the number of operation by 2. Again, also sparse matrix over. That means if you have something called skyline, in other words, I'm only storing the highest value of this in the matrix, and they will fill in all the underneath. So I don't have to store all the elements above this. So this was also the problem initially when I was doing my PhD at Berkeley in the late 80s. It was, I had either a root account, and I had 4 megabytes of space on my disk for me, at 4 megabytes space for a printer. and all the colleagues that have only 4 megabytes of space. So you can imagine if you have 4 megabytes of space today on your phone, you have gigabytes and stuff like that. So the things have changed a lot, but still, still you have to worry about the storage because also the ambition has changed a lot because now we're talking about solving billions of equations opposed to before when you solve a couple of thousand, you're already like a big boss. So anyway, the idea is what is probably the best feature of Gauss method is that you give you a condition number very clearly. So what is the condition number? The condition number is the sensitivity of problem to how careful you should be when you're computing the solution. In other words, condition number is the ratio between the largest eigenvalue of your stiffness matrix and the smallest eigenvalue. What is eigenvalue? Eigenvalue is the solution to eigenvalue problem. We take a stiffness matrix minus lambda I is eigenvalue matrix times identity matrix times VI. VI is a corresponding eigenvector, and then it has to be equal to 0. The solution to this is lambda 1, lambda 2, all the way to lambda n, the number of these equations, and then lambda 1 has to be the smallest all the way to lambda n, which is the largest. So the ratio between largest and smallest eigenvalue is already something that we call condition number and gives you how much the things can go wrong when you're doing computation. In other words, in real engineering problems, we do not really know the exact loading, either because of uncertainty or because we did not measure this correctly. And so happens that actually instead of real problem and real loading that we have to apply F external, we actually put a little bit more perturbation either up and down. So the interest is that the solution this way is not going to explode. And basically this you measure by the perturbation of the displacement, nodal values, as opposed to the norm of this displacement. It could be Euclidean norm. You take each and every component of this vector, multiply by itself, sum it up and take a square root, and that would be it. It so happens that the perturbation versus the computed result is bounded by the condition number. So if you have a structure which has a very large stiffness in one direction and very small stiffness in another direction, so basically I have like something like this shell. So it has really like a very small stiffness in the bending case and has very large stiffness in the membrane case. Basically, I can really have a huge influence on the computed result. So shells are notoriously complicated when you're computing the solution, and so are something that we call the softening phenomena, because once you go into plasticity hardening, they can go to stiffness, you come with the elastic case, and you go to plastic case, you go down to 0, even to negative values, and again you have very large perturbation. The same perturbation applies to the structure, namely, if you do not really quantify the structure correctly. Why would that be the case? Either you don't have a geometry correctly, or you don't have material properties, which is more likely defined correctly, then basically the condition number will give you how much the error in quantifying the structure stiffness matrix will be amplified in computing the solution. Again, you want something that is reasonably under control and the things of this kind. So Gauss method gives you the chance of knowing how much, let's say, precision you should be using when you're computing the thing. So it used to be like people could do computation single precision, but now it's like double precision already standards. And if you start mixing like we did in a framework of thesis, so one of my really good students, Pablo Moreno, basically the idea is like mixing electromagnetism and thermodynamics. So in mechanics, you have heat transfer, you have electromagnetics and stuff like that. The order of magnitude, different units that you use in mixing all these different domains is so big that sooner or later you end up comparing, something which is 10 to the plus 20 as opposed to 10 to the minus 20 and stuff like that. So you really come to the case where whatever you do, you come really into trouble. So you have to be, when you start mixing different physics and different scales, what is called in space and time, of the typical behavior of these fields that you're computing, one really has to be very careful and use the best possible solution scheme. Now, this was an all linear system, and if you haven't seen Gaussian method, I hope at least with these 3 steps, you can recover it, and you have it in the book in more detail. Now, what happens when I have a nonlinear system? I don't want to be too fancy. I simply try to get the first approach, something that I already know from linear system. So the goal of something called incremental analysis is to make look nonlinear problem like my linear problem. How do I do that? First of all, I introduce something called pseudo-time parameter. This pseudo-time parameter serves to describe the loading program. So I start loading at time t equal to 0, and I go to uppercase T. So basically, I will focus with incremental analysis upon one increment at a time. At one increment is something going from Tn to Tn plus 1. where the sequence of the increment is 0, t1, t2, tn, tn plus 1, all the way to uppercase t. I take as many increments as needed to get my solution to be reasonable. What does it mean? That means that my true nonlinear problem look as much as possible as like a linear problem. So basically, this would allow me to take an equivalent solution to the nonlinear problem by using a sequence of these linear problems. So how do I do that? Well, basically, typical case is if I take external loading to define as a fixed pattern of the loads multiplied by some kind of time variation of this loading, I can get my incremental load as a value of external load n plus 1 minus n, and that amounts to saying the fixed load times g tn plus 1 minus g of tn. And I have an exact representation. If I take something like a g of t equal to t, I actually have exact representation of the variation of the external load. Typically, I take, there's no reason not to take that in most of the cases, to simply increase linearly, unless you have some kind of other, let's say, input on how you do it. So the point now is a tertiary step. I have defined the increment of the external load, and I have a starting point of my displacement. So in order to change notation a little bit in a better way, I'm calling now this displacement time Tn, dn. So this is the value of nodal displacement time Tn. And then the goal would be to increase this displacement to the next step, or decrease whatever it is, to change it by the incremental displacement. So now I'm calling un plus 1 would be incremental displacement, rather than calling it big delta times dn plus 1 to simplify notation. I'm now reserving u to be incremental displacement. So in the linear analysis, when you have only one increment, I can go back to my previous notation. In nonlinear analysis, now d would be the total displacement, and u would be incremental displacement. And you need these indices to handle this and each and every particular increment. So typical increment going from Tn to Tn plus 1 is as follows. I know the stiffness matrix time Tn because I know the displacement value at this time, so I can compute anything I want, even if it's nonlinear analysis. And I know my increment of the external loading going from Tn plus 1 to Tn to Tn plus 1. And I'm computing this incremental displacement n plus 1 when it's superposed on Dn, the previous displacement, will give me displacement n plus 1. So basically, this is done as follows. I'm again using simply Taylor's formula, saying that if I take a development of some kind of function, scalar function g of a scalar argument x, that will be like a value of this function at x bar plus the first derivative times the increment. So this is illustrated here. This will be a true function, the thick black line, going from x bar to x bar plus u. And the linear approximation will be like the value at x bar plus the first derivative times u, which amounts to this one. So linear approximation obviously is not the same as this function. On the other hand, has the advantage of giving me only linear interpretation of this problem, which now I can solve by using standard methods like Gauss method and so on and so forth. So in each increment, I'm making a mistake, which is proportional to the second derivative of this function, obviously. And basically, how can I get rid of that? Well, I cannot, but I can make it as small as possible by taking small increments. And that will be hopefully good enough to solving my problem. Now, this was a scalar function with scalar argument. But actually, what I typically have to do, I have a scalar function, which will be like this internal work and stuff like that, or potential energy, depends on this Gaussian read, so finite element. And basically, it's a function of vector argument. So now I can do that again, directional or Gato derivative. I can take my pseudo time t, multiply by the incremental displacement to get corresponding derivative. And so this becomes the same as this variation. So that amounts to saying I have a value at the fixed value of x bar, plus the first Gato derivative would be equal to 0 after that. And basically, I'm getting something like this. I'm getting this w times the internal dn, function of dn, times f external n. And this amounts to getting my linearization that is written as such. You have WA times KAB, function of dn, times UB at n plus 1. What it means, I have computed here the so-called tangent stiffness matrix that corresponds to a particular value of the displacement dn. And instead of the linear problem where I always keep the same, let's say, Young's modulus, in this nonlinear problem, I'm looking for a corresponding value of the nonlinear tangent modulus. And for the given displacement dn, I'm computing given strain and computing the corresponding tangent modulus and computing the stiffness matrix with it. So in the truss bar, that will always E over L or E A over L. when it's a linear analysis, but here will be, instead of E, you will have a C hat, a function of your displacement times A, if you have it, and then divided by L. As simple as that. So really, there's not much to that rather than this incremental analysis. Now, using Taylor formula, what you can say is that you have the best approximation, like a quadratic approximation of your function. In other words, that difference between the internal force at n+1, internal force at n, compared to tangent stiffness at then dn times the incremental displacement un+1. The norm of this vector is smaller. It's actually quadratic compared to the norm of the vector u. And so you can actually get, let's say, as a rather good approximation of this. This will be like the best approximation in this sense here, if you're looking for this residual. So basically, what then incremental analysis would mean? Look at the typical time step. So at external force, you have a value of n plus the increment that you have produced by using the fixed value of this load parameter, F0 external, then G of Tn plus 1 minus G of Tn. Okay? Now, in internal forces, I have this tangent stiffness, and basically I have written my internal force as the value of time Tn plus the tangent stiffness at this time Tn times incremental displacement. Then, how can I get my final solution? Is basically, well, final equation to solve. I'm assuming that I have equilibrium at the previous step, that internal forces and external forces are match. In other words, this and that term can cancel. So from the above equation, I can obtain a tangent stiffness computed at time Tn times the incremental displacement un+1 equal to the increment of the external forces. And that is simply the same thing as my Gauss problem here that I had before, that Ku is equal to what you call it, Ku was equal to external force. And I was doing this with the triangularization, then forward direction back substitution. So in each and every of these increments, I'm solving the same type of problem. The only difference at each increment, the nonlinear behavior, elastic behavior, changing the stiffness matrix. Previously, I had it one and four computed. Here, I had to compute it in each and every increment because displacements are changing, and so is the tangent stiffness. So basically, by computing this incremental displacement for this particular increment, I add it on top of the previous displacement, and I keep going forward. So if I exhaust all the number of increments that I've chosen, I finally deconstruct my solution. So what will it be like? The real solution is this thick black line. This is a nonlinear function. Let's say if I have this quadratic behavior and so on. But in this incremental solution, I have these three increments, and there's every of these increments, I have a corresponding linear solution. Please note here, I had tangent stiffness computed at 0. Then I get my incremental solution. I have this is my displacement. Then I have a tangent stiffness computing here at this point, and I'm putting on top of that. Then I have tangent stiffness computed here. This one is the same as this one, and I'm computing there. So you can see that in each increment, I produce incremental displacement, adding on top of the previous displacement. And this way, I'm constructing the response, which happens to be piecewise linear, because in each increment, the response is linear. Piecewise linear is never the same as really truly curvilinear response. And a typical situation is really the one which is pictured here, that I basically have in each and every step, the true solution deviates from the real solution. But if I'm studying the cases that are very short in time, namely something like a problem of explosion or whatever, the attacks and stuff like that, or of this kind, in this case, we are using something called explicit codes. And this is the typical situation that people are using. In this case, typically, you're talking about a fraction of a second that whole procedure takes place. And then the time steps are 10 to the minus 5. So in 10 to the minus 5, when you start making mistakes, you do not accumulate as much. However, these explicit methods nowadays have been used into phenomena in time integration that are much longer. For example, recently I had the chance to be in this anniversary conference in Mexico. It was held in Acapulco. It was a famous, sadly famous earthquake that in '85 brought really lots of damage to the city. And then 30 years later, we had this presentation. So I was one of these speakers, and the other guy was a British guy who was using it on a 3D. This is a very famous explicit code. It was built by the US Army laboratory to test the efficiency of the weapon that these guys are producing for the explosion, something like that. And all of a sudden, he was using that for earthquakes. And some earthquakes today, if you go to Chile, they last 5 minutes, you know. So you can have a very longer period of shaking. So if you accumulate errors with explicit method during 5 minutes, obviously the result is worthless. On the other hand, it's much easier to compute. And then people are doing that in some way. So one has to be careful. We'll talk about that as we go along. But anyway, just wanted to warn you about that. So at this stage, we haven't done nothing else, but just said that nonlinear elasticity can be treated just like a sequence of the linear elasticity problems. We split this true behavior into a number of this linear type of behavior, and we know how to advance by assuming basically that every time we linearize, we get the corresponding tangent stiffness, we compute incremental displacement, we put it on top of that one, and so on and so forth. So you have at least some solution. And the solution is better than nothing compared to many other nonlinear problems which are hard to solve. This one at least gives you some chance of solving it. Now, if you're not happy, and in a situation you cannot be, because if you need some stringent type of requirement, something like, you know, you have a nuclear power plants, we worked on that for many years, and you want to keep it going on for many years, and now coming back after Fukushima, they was all abandoned, but now they're really coming back very strongly because people need electric energy. So many countries are increasing number of reactors they're using, and so on and so forth. So basically, you want to make sure that when you compute, you can get as close as you want to the true nonlinear solution that you have there, even if you're using this piecewise linear solution. So what's the trick? Well, I don't have to stop with incremental analysis. I can say, okay, here I made a mistake, here I made a mistake, here I made a mistake. So what is the way to correct this mistake? Well, first of all, I can say that this is residual, the difference between true, let's say, level of the external load and what I'm given with internal load. Obviously, this is not equilibrium. This had to match. I have to come to this point. So how do I come to this point? Basically, I can say, okay, when I notice that the difference between the internal force at the given value produced by incremental analysis and the external force is not zero. Now, when you talk about vector, you have to define what exactly do you mean it's not zero. It has to be some norm. It could be normal vector, it could be some norm other. We'll talk about that in a second. Then you improve this by iterating. In other words, you stop your incremental analysis, you fix n, and then you iterate. So the first iteration will be you have this residual, and this is producing you the first iteration of your incremental displacement. Obviously, this is not good enough because residual difference between external force and internal force, this will be the value here, is not close enough, is not close to zero. So then you repeat the same trick like incremental analysis, only this time around, you compute the tangent stiffness not only at dn, but dn plus un plus 1, the value which was given to you by incremental analysis. And you take residual, which is different between the external force and the internal force, which is produced by the incremental analysis. And this feeds into the second iterative improvement of your incremental displacement. And then even if this, again, allow you to compute internal force, and the difference between external and internal force is not small enough, then you make a next iteration, next iteration, next iteration. So what really, at the end, after all these iterations, what you actually recover is here. This was reminder what we've done with the incremental analysis. And we go from one step to another. But now this is your iterative improvement of your particular increment. So I took a single step between d and d plus 1, and I blew it here. So basically, with the previous solution, I made sure that internal external forces are matching. So I'm starting from here. And then I want to do this the same, that internal external forces are matching. So I do incremental analysis step. I'm here. The residual is not zero. This is my first iterative residual. This is the one that we feed into here to get the second iterative improvement of this displacement, which is here. Then I linearize again, all the way until I'm happy in terms of difference between external force and internal force. What do I mean by being happy? Well, basically, I have to have a norm. The norm could be simply the Euclidean norm of the external force minus internal force has to be smaller than tolerance. The tolerance will be as small as you want to have some kind of decent value of your solution. And so I can typically combine, these are called Newton's iteration with incremental analysis. That is basically I start with each increment with dn plus 1 first iteration equal to dn. Then I compute for the first time something like incremental analysis. Then I get a improvement for my total displacement. Then I go back here if this is not good enough, and so on and so forth. I keep iterating until the tolerance difference between external and internal forces is small enough. So basically, this one is really like something that would give me the improvement, so I can get as close as I want to the true nonlinear solution, and I will get all these points one by one and retrace the whole type of solution for each and every increment, not in between, but for each and every increment I have it. So basically, one possibility is to have this tolerance check in terms of the forces. But if you have something very kind of soft and you go into what's something called saturation hardening, it turns out that the difference between these internal and external force could be very small, yet you are having like a still very large iterative contribution to your displacement field. And in that case, another tolerance could be used that is like the norm of the incremental iterative contribution of displacement field. If that one is smaller in tolerance, you can do that. Or this one again is not good if you have something like hardening. If you have this kind of rubber like elasticity, you can have very small incremental iterative contribution to displacement, but you can have very large contribution to your what you call it internal force or residual. So the best maybe goal is to have a product of these two. At the same time, you're computing the increment of each iteration, and you're computing the residual. And you make a scalar product redo. This is like energy-like norm that you might take. So if you have done, like either this choice or incremental displacement choice, and you keep it 10 to the minus 5, then this one should be 10 to the minus 10 because it should be product of these two. So typical values are really something that should be quite demanding in order to make sure that the results that you're doing is really the one that is kind of credible. So Newton method doesn't need incremental analysis. Once you are using Newton method, you can converge in one shot. In other words, you can apply all the loading in one shot, and then you iterate. And in each iteration, you have something that is called reducing the residual by order of magnitude 2. That is, you have something called quadratic convergence property of this Newton method. It's very easy to show if R of D is an exact solution, and your iterative solution is given like that. Basically, you can express the exact solution in terms of iterative solution by using this approximation as some kind of second derivative value of psi bar, which is between di and d bar. And then from that one, you can work it out and so show that this is really simply your way of producing your next iterative guess. And then basically that becomes equal to the difference between d and di, d bar and di, d bar being the exact solution, and di plus 1, this is next iterative sweep, and d bar is basically proportional to the square. In other words, in each and every iteration, the error is reduced quadratically. What that means is basically if you go really close to the zero, you will recognize the performance of Newton's method by saying that behind decimal point, the number of zeros will double. So there's 1, then there's 2, there's 4, the next one will be 8, and so on and so forth. It doesn't have to be really that one, but it has to be close to that because it also depends on the regularity of this term here. Now, this is great if your Newton method is kind of converging, but as much as it's converging quadratically, this also can go and diverge quadratically. Typically, if the first guess is lousy and is not so good, then you can go away from the real solution very, very fast. So better, you stick with that and try to keep it like under control in a sense that you get really a good result. So combining incremental analysis and the Newton method is always a good strategy, especially when you have like a large variability of the loading and so on and so forth. So this is, let's say, the first part of the story of the technology of finite element method. Most of the codes are using the kind of robust schemes for solving the set of algebraic equation. This is the final product of finite element discretization. And then they use some kind of different iterative methods when it's nonlinear and so on and so forth to kind of, in essence, this is kind of in the crunch that I try to explain. Now, the second point has to do with the constructing these what I call technology of finite elements, has to do with constructing these finite element arrays. This is the stiffness matrix K, internal force, external force, and so on and so forth. Now, this is not done by integration, at least not by analytical integration. It is done by something called numerical integration. And this is the invention of late Bruce Irons, who was one of these really important scientists who worked in the team of Oleg Zinkevich. That was good old times where basically Zinkevich hired Irons while he was working for Rolls-Royce and brought him to his team in Swansea, which is basically going from London to Swansea was really like a big deal because compared to London, Swansea definitely not as exciting. And secondly, going from industry where typically they pay a lot to be a scientist, but I was a scientist, so really he kind of built two important things for the technology of finite element method, which is basically the isoparametric, let's say, representation and the numerical integration with the patch test and so on. So his legacy is firmly confirmed, I would say. Although not everything that he said was right. We talk about real rotation, but I won't talk about that. This is for the guys doing structures. So what is that we are talking when we talk about this, what I call technology of finite elements? This is typically how the software is built when you're doing that. So typically, your goal is to build a set of equations, which is K at every iteration I, stiffness at every iteration I, times the incremental displacement at iteration I, equal to this residual iteration I. And we are talking about these shape functions for two-node truss-bar elements to start with, very simple. So if I take this shape function to be a function of x, which is a global coordinate, basically then I have to worry for each and every element which has different coordinates and different way of constructing this function. Please recall, is it written here? Sorry about that. Let me go back very quickly to remind you. The shape function was a kind of, sorry, but there, where are you? Okay, it's here. See, the shape functions are kind of the function that vary for each coordinate xa and xa plus 1 and each length and so on and so forth. So I really have to do like each element becomes like a different type of problem to worry about. Yet when you are doing your computations, where you're really becoming very efficient is if you keep doing something over and over again and do it very quickly. Unfortunately, many of these production environment, that's the main goal. Keep doing something very quickly and do it over and over again. So the goal is now how to make each and every element, even if they have different nodes and stuff like that, if they belong to the family called two-node truss-bar element, they're all the same family. They're going to be treated all the same way. In other words, in your typical code, you'll have a piece of code, often called subroutine, where you actually do the computation for this particular element. And you have one for two-node truss-bar element, one for two-node beam, one for shell, one for this, for that, and you simply choose this one. What you're really doing, you're choosing your shape function. You're choosing what kind of approximation you're making for your displacement field. And then the second point is like, okay, I have to integrate in the physical domain that goes from xa to xa plus 1. Now, I don't want to talk about this immediately. I want this domain to look always the same. So what I do transformation coordinates, where this domain of any typical element, two-node truss-bar element, will be the same. So basically, I'm now transforming this. First of all, I take the whole domain, omega. I split it into the number of subdomains called the elements. So my typical problem to solve is integrating all this typical element omega e with the shape function a, or whatever it could be, squared or whatever it is. And then basically, I want this to be, once I split it into these subdomains, I want this now to be treated in the same manner. In other words, I'm now changing the coordinates. I'm taking so-called these isoparametric coordinates, or natural coordinates, if you want, what I call the xi. And basically, by changing the coordinates, I'm expressing this change. Dx would be j xi dxi, where j would be Jacobian changeable coordinate. And I have this function, which was function of x, becoming function of xi. And now the reason for that is that each and every of those elements, for me, is no longer going from xa to xa plus 1, but it's going from -1 to +1. -1 plus 1 is the bounds chosen because of numerical integration. We'll come to that in a second. So basically, the idea is like I have something called global description, and I have something called local description. Local description has for the goal that make every of these elements to appear to be the same. So I place it between xi1 and xi2. I just said xi1 is -1, xi2 is +1. My nodes are called 1 and 2 because it's only two-node truss-bar elements, so I don't care. It's just 1 and 2. I don't need any other numbers. My degrees of freedom are D1 and D2 with the index E to say this is element point of view or local description. My shape functions are n1 and n2, which look the same like this nax and a plus 1x, only they're expressed in terms of psi, where I have to establish connection between x and psi. We'll come to that in a second. And so my displacement field interpolation is not done in terms of x, but it's done now in terms of psi, where these shape functions are functional psi, natural coordinates. So how does it work? Well, basically, I have to find the connection between x and psi. Now, these are two no-transfer elements, and shape functions are only linear polynomials. So whatever I do, I'm changing from linear polynomial to another linear polynomial. So x of psi could only be a linear polynomial, which is c1 plus c2 psi. c1 and c2 are constants. So how do I fix them? Well, I can match the endpoints. I know that if I want to express geometry at psi equal to -1, this is left end of this element. This is coordinate xa. And for psi equal to +1, this is the right end of this element. This is xa plus 1. So for these two simple equations, given x to be c1 plus c2, and given this -1 plus 1, I obtained that c1 and c2 could be expressed as xa plus 1 divided by 2, and c2 will be equal to le divided 2, but le is the length of the element, is xa plus 1 minus xa. In other words, I'm simply shifting the origin of my coordinate system x to the center of this particular element, and I'm changing the metric. Metric is the length. I would actually measure the distance in space, so that the length of this element, which is really L, becomes equal to 2. Again, this is done for the numerical integration. We'll see in a moment why we do that. So the key role in this one, as you see when you go from one the integral to another, is this Jacobian transformation. So Jacobian transformation is the derivative of this function x with respect to psi. So when you take the derivative with respect to psi, this is just c2, and c2 is nothing but le over 2. So basically, when you go to natural coordinates, or as a parametric coordinate psi, you appear, you make every of these Strasbourg element appear to be equal to 2, and handle with the coordinate system, which is placed in the center element, and so on and so forth. So this is the way you start constructing your field. So now you have local or elementary transformation, which are using basically this. So to start with, I'm going to construct the element interpretation of stiffness matrix and element interpretation of the external force and internal force. How does it work? So basically, here's my shape functions. One way to representing them, it would be to be equal to n1 is 1/2 1 plus psi. So 1 minus psi for a equal to 1. And then n2 is 1/2 1 plus psi for a equal to 2. So my domain interpolation could be done by x of psi is equal to n1 times xa, x1, and then n2 times x2. So in x1, I field xa, in x2, I field xa plus 1. And then I take the same shape function, and I interpret the displacement field by using these nodal values of that unknown for displacement. Again, these functions are 1 for the n values and 0 for all the other values for this particular one. So basically, they are called isoparametric because the same shape functions are used for the geometry and for the displacement field. They happen to be very handy and very comfortable when you do large displacement, because then you simply slam on top of your coordinates, you slam this displacement, you keep producing new deformed configuration with large displacement, so on and so forth. So it really fits very nicely into this description. So basically, I do the same thing for the virtual displacement. In other words, I'm using the same isoparametric shape functions, NA of psi, just multiplied by the nodal values of this virtual displacement field, and I have my say virtual displacement there and final. So once I have interpolation for my true displacement UH and my virtual displacement, I will need to compute the true deformation and the virtual deformation in order to go into this computation of integrals. And so now the problem I have is that epsilon is still the derivative of the displacement field with respect to x. But now u is no longer expressed as a function of x, it's expressed as a function of c. So I can still go around that. I write this that in of c dx times dA is actually the same as 1 over dx over dxi, which is nothing but my Jacobian dx dxi, and it happened to be le over 2. And then basically, I here get dna dxi, which is easy to compute. It's either, -1 times 1/2 for the derivative of the first, or +1 times 1/2 for the derivative of the second. Then dx dxi is L over 2, which is 2 over L. So when all is said and done, this becomes -a to the power A being 1 or 2, divided by E times VA. So this is nothing again but D2 minus V1 divided by LE, just like we had it already for the strain. So the fact that we have changed the computation, it doesn't mean the end result changed. It just means that in the processes of these computational results, we have done something which allows us to do uniform computations. There's no approximation here, it's just change of coordinates, which is handling this in a systematic manner. So you can do a single piece of software called subroutine to compute all the stiffness matrices, all the internal forces, all the external forces for each and every truss bar element with 2 nodes, no matter what is the coordinate and what is all this. And in 1D, it's no big deal because you can do that otherwise, but in 3D, believe me, it's a big deal because then it simplifies the problem a lot. These are the parametric elements when they were introduced by Zinkiewicz, Irons, and so on and so forth. They really had a huge success. That was the first book of Zinkiewicz, and that really was sold in a very large number of copies because the first time people trying to do this in a systematic manner. So if on top of that, Berkeley people had really good codes like SAP, my other supervisor at Wilson, and then many people got these codes you could buy at that time for $400. And then they built something like called Cosmos, whatever it is, then a bunch of the other codes, but built from the student codes at Berkeley, that really had very large diffusion. So you could really had a chance to learn a coding plus on that computation again, but you had more than one course on doctoral school. I had the 25 courses. I kept taking courses all the time. What the hell? Well, okay, we did this computational without strain, then we can go to the computational internal forces. Once I have a strain, which is computational, the shape function BE that was just explained here times this, you put this in computed strain, you stick this into the rule for computing the stress, and you multiply by the derivative of shape function BA. And basically you get this to be minus A to the power A divided by L times sigma, and here you have a dxi is L over 2 times dxi. So if you take this on the integral, let's say this is a constant, so this will be constant as well, you take it out. Here you will have L and L will cancel, and you have an integral from -1 to 1 that becomes 2, divided by this 2 is again 2. So at the end, all is said and done, internal force in stress bar is either minus the stress, which is constant, or plus the stress is the constant. Minus is the first node, plus is the second node. As simple as that. And then the stiffness matrix, you remember the usual stress bar stiffness matrix, EA over L. Here is the same thing. It's like a EA over L, only E keeps changing for every value of strain. So I have like a C, like a tangent modulus, which is a function of the current value of the strain. And then will be like over L, it's like plus or minus 1, depends where you are, 1, 1 or 1, 2, 2, 1, 2, 2. And the A would be cross section that I put on top of that if you are really to use it. So basically, this is the kind of thing that you go automatically. Now, internal forces and stiffness matrix do go together. And if you go to more complicated situation like inelastic behavior, plasticity, and so on and so forth, they will have to be integrated precisely in the same manner because both of them depend on the so-called internal variables like plastic strain, damage variables, and so on and so forth. External forces, they don't really care. And you will see that in a moment what can be. But before I go there, I wanted just to comment on some conditions that have to be respected when you switch from physical coordinate X to the natural coordinate Xi. And you have to respect so-called consistency or convergence criteria of the finite element approximation. What that means is simply give you a guarantee that when you do the switch, you can actually do this computation correctly. So first of all, it's a practical. NA should be C1 at omega E. What that means, typically in the stiffness matrix or internal force, you see here you have a derivative, here you have a derivative again. In the internal force also you have a derivative and so on and so forth. So basically you want this first derivative to be computed from shape function to be continuous function. That means you don't have to split your element in the natural coordinate system in some kind of subdomains because throughout this domain, it's the same function that you're using. And that's a kind of practical requirement because you don't really want to be able to do that. And many methods, like something called XFEM, this is semi-finite element, they have to split this, really juggling. They really solved it. This was like a XFEM was really very skillfully solved by later Belichko solving this fracture problem and so on and so on. Many people in France are using it. But in fact, you know, they give you like representation of crack on top of your field and so on and so forth. But the problem that really is completely messing up the structure behind how you actually compute these finite elements and stuff like that. So for the moment, we start with the idea we don't have any extension to this, no expanding or voting. We'll talk about structure later. And basically, the idea is that here you have to have this smoothness. When you go from one representation in function x to function xi, both of these are smooth enough to get any derivative you need. And here in particular, it's only first derivative. Now, second point is that when you go from one element to another, that means you span the whole domain omega. Here was only omega e. Here notice omega. The function have to be C0. What that means is then one approximation of one element and the other approximation of the next element have to match each other. But this is automatically ensured because they share the same nodal values of displacement. So basically, the idea is like if they don't match each other, you get something like this expand. That means like jump, like a discontinuity of displacement. So discontinuity is treated by Heaviside function, and Heaviside function derivative is so-called Dirac function. If you didn't have the detail, you can check it a little bit in the book and whatever. And Dirac function is used, for example, in dynamics level, impulsive loading, and so on and so forth. So Dirac function integrated over any domain from -infinity to infinity will give you just the value at the particular function. Namely, if I take Dirac centered at x minus xc times any function f of x, I'll get just the value of xc. That means it puts infinite weight on the value of xc. That's actually as simple as that. On the other hand, if I have Dirac square, why would that be Dirac square? Well, because in stiffness matrix, I have these derivatives coming 2 times, here, there. So if it happened to be the same one, I will have Dirac square, but that one, I don't know what it is. So the continuity of the shape function from one element to another has to be ensured. So in 1D, it's trivial, it just comes to the same node, but in 2D, 3D is actually that the approximation along the edge, which is separating 2 adjacent elements, has to be continuous. So in the higher order elements like shells and stuff like that, this was really one of the biggest difficulty when people are trying to construct their interpolations. So, okay, then the last the requirement, the sum of all these shape functions over a particular element has to be equal to 1. It's a very simple one. That actually amounts to saying if all the displacements are the same, be constant, then I have to impose that the sum of these NA equal to 1 because now C0 will be motion of the rigid body this particular element, and you want that computed displacement also has to be the same thing. So if it's not, then you are really in trouble. So basically here, typically this is the kind of requirement to compute internal force and tangent stiffness matrix. Now, requirement to compute external force, you can certainly imagine a very large variety of different loads that could be applied to your structure. And you can certainly compute something with whatever it is, the load that you might want to apply. However, for practical purposes, it's much handier to describe the load by using the same shape functions. Although there's nothing really essential here, there's no physics, there's no mechanics, there's nothing there. It's just a convenient way of describing the load so you don't have to worry about getting also some kind of function defined. So we recycle the same shape functions and we describe the load to be applied by using the shape function that are used for the displacement field, which has nothing to do with load, but just practical, times some kind of nodal values, and you get the description of your loading. For example, if B of xi is constant, well, basically there's nothing. N will be 1, and there will just this be A, and that's it. But this way, for 2-node transbar element, you can have like a linear variation of the loading. You can not have more than linear, but with L, if you really need something more, you probably 2-node transbar element is not good enough for the computing your solution. So the fact that the external load is also described by using this type of shape function is not a very surprising type of phenomenon. So now, if you take this one, you can compute that the corresponding loading, you see, if you have linear distribution, it will be at the end when you go through this computation, this is your interpolation of your loading, this is your shape function that comes from the virtual work. So this is what I was saying. It's not simply like take a half, but it's something like a final result will be LE over 6, where L is the real length of the element. Here's 2B1 plus B2, and here B1 plus 2B2. Namely, the idea is that this type of thing is a equivalent loading, which is really a representative of what this external load will be doing as the work on your particular virtual displacement in order to get a full understanding of what is the consequences of applying this load. So this really amounts to computing all the elements and all the arrays for this particular element. Now, if you're not happy with 2-node transbar element, you can go more ambitious. You can go for the 3-node. You can go to n nodes. all these elements could be increasing the order of polynomials and getting faster approximation to any variation of your displacement field. So for number of element nodes, any n given to whatever value is equal to 2, easy way to construct these shape functions. Again, for each and every node A, it has to have unit value, and all the other nodes has to have a 0 value. So you can use so-called Lagrange polynomials, which are basically product of these monomials, where you have here xi, your natural coordinate, minus xi b, where b is all the other nodes but the node A, which we're interested in, divided by xi a minus xi b. So you can see if you develop what it is, this is written here, you can say that for every value other than xi a, this will always equal to 0, because there's always one of these guys who's sitting there, the monomial term will cancel. And for the value of xi is equal to xi a, what you have up is the same as you have down in the numerator and denominator are the same. So basically you have NA equal to 1. So if I illustrate it for 3-node truss-by element, this will be now your approximation. Again, the domain always goes from -1 to +1. And basically you have this quadratic form, and you have this kind of variation. So here I will have this one to be 1/2 xi times xi minus 1. Obviously, it's 1 when xi is equal to -1. It's 0 when xi is equal to 0. It's 0 when xi is equal to 1. The same thing here, only upside down. This will be 1 when xi is equal to +1, and 0 when xi is equal to -1. And the final shape here is like this bubble function, which is in the middle. This is 1 minus xi squared, which is 0 when xi is equal to plus or minus 1, and 1 when xi is equal to 0. Now, you note that in a 2-node truss-by element, the Jacobian, which is dx dxi, was constant, was the length of the real element, LE divided by 2. A 3-node element, this is no longer the case. Now, Jacobian is a linear function because it's a quadratic. You take the first derivative, you get a linear function. In other words, Jacobian, the way you measure distance varies along the element. And so that makes some additional type of tricky things when you're choosing these high-order elements, because you have to worry about, let's say, Bell positiveness of this problem. In other words, when you're transforming from the space X to space Xi, the real element, which might have these nodes in natural element, parent element was called, is always nicely placed, -1, 0, +1. But here, it doesn't have to be. You can sometimes shift the node because it's more handy to put some kind of concentrated load here. And then when you're doing this, you should never really push it too much. You should never leave LE over 2. Why is that? Because in each and every of these transformation from the natural to real coordinate system, Jacobian has to be positive. In other words, how you measure distance has to be positive. When you say something is 2 meters from you, it's 2 meters from you. It doesn't exist in the notion -2 meters from you, because you don't have orientation. It's just like a distance. So distance is norm is always positive, so it cannot be negative. So if you have Jacobian to be negative, that means you're turning a positive norm into a negative norm, something goes wrong. In other words, transformation from X and Xi is no longer bijection. For 1 and 1 point only in Xi space, you don't get 1 and 1 point only in X space. And then everything goes berserk. And that happens more often than you think. So in 3-node element, Jacobian is this. So if you really want to put extremes where Xi is +1 or Xi -1, that would amount you to say that X2 should never be smaller than, this is the center of the element, X1 plus X3 divided by 2 plus L over 4, or it should never be bigger than X1 plus X3 divided by 2 minus L over 4. In other words, this is the picture. You should stay inside this 1/2 in order to get the true computation. Now, if you now build your interpolation by using this strain, this interpolation function, that I can compute my strains, I can compute my stress. Again, the whole thing is computed by taking the derivative of this shape function of Xi and divided by J, which is no longer constant, and so on and so forth. So very soon it becomes kind of a little bit more strenuous to compute. Even if you have polynomials, you end up having a rational function because there's just 1 over J that's meddling in. So the numerical computation of these things is not so easy. Rather, analytical computation is so easy. So we turn to numerical computation. This was the invention of Bruce Islands again. What if you do is the following. These are the real functions you want to compute. There's an end function and shape function in the natural coordinate space, or their derivatives, and basically Jacobian and so on and so forth. And you actually first approximated this function with some kind of polynomial. So this polynomial goes also in the same domain from -1 to +1. And this polynomial is chosen to match the real value of function in a certain number of points. These are points are called abscissa. And then you integrate this polynomial, you match the true function set number of points, and you write the result in terms of this weights times the value of the abscissa. So the real function, let's say f of xi, and the polynomial function g of xi have the same value as the chosen values xi l, which are abscissas, and then weights are something that you have to compute from the matching these two results. Let me illustrate this in the two-node element with the one integration points. So we have basically g of xi has to be linear with constant c0, c1. So basically I have a w1 g1 plus w2 that will be integrating this polynomial here. And so if I really want to do that, turns out that basically 2 of g0 has to match 2c0. So I can see that for this case, c1 is equal to 0 and w1 has to be equal to 2. In other words, I can have any variation of this. Let me just illustrate what I mean by that. I can have I can have this is my element, let's say here, and basically this is the kind of integral I'm trying to obtain. This is my true function f of xi, and I'm simply taking a straight line and approximate it like that. This is my g of xi. So these two have the same value at the single point, which is here. So I can then say the area of this trapeze is at xi equal to 0, because this is 1/2 of this plus that, and then height is actually equal to 2. And that's precisely what I get. So basically the idea is like the idea really comes to that immediately, that basically you get the weight of this integration equal to 2 and the value of the function xi is equal to 1. Then if I go to the 2x2 integration points, that I can accommodate, I have 2 weights and I have 2 abscissas, I have 4 unknowns. So I can obtain 4 unknown coefficients c0, 1, 2, and 3. That means I can accommodate a cubic polynomial. By matching these two values, I can get that the weights are equal to 1, and xi1 is equal minus 1 over square root of 3, and xi2 is equal to plus 1 square root of 3, and they're actually matching each other. So when all is said and done, in order to compute my integration points, to compute my internal force and tangent stiffness, I'm not integrating anything anymore. I'm simply taking the values of the function that is defined here to be integrated and taking the values at the particular abscissas, the particular Gauss points. If it's 1 point, I only take a 0 and derivative is 0, stress is 0, and multiply by weight, which is equal to 2. Here's Jacobian, and I get back minus sigma or plus sigma for 2-node Strasbourg element. If I have a 3-node, that will become a little bit more complicated and tangent stiffness as well. Now, what's really important to do for 2-node Strasbourg, it's enough to have 1 point. For 3-node, I have to have 2, and you can check this a little bit in your computation to play with. But the idea is like external force, I have to be more demanding, because if I take for 2-node Strasbourg element only 1 Gauss point, I get this loading to be LE over 4 B1 plus B2, which is not correct if you compare what I was giving you before with the exact integration of the loading for the linear variation load. Obviously, this is not right. So for this one, you need 2 integration points. You want to get it right, and then you can really have the kind of result. So please note that this isoparametric interpolation is so-called continuum consistent interpolation. What it means, if I have nonlinear problem, typically you should first be discretizing and then linearizing. However, in this case, given that the interpolations are linear combination of nodal values, discretization, linearization commute, so I can still carry on with the linearization, the continuum problem, and then discretize. My end result will be the same, which is kind of big advantage for this type of situation. It's not always the case. For example, for the beams, I was just dealing recently with some kind of rotation stuff. Late Mike Trissy was doing this nonlinear stuff like that, and basically turns out it was simply not isoparametric interpolation, but something else. So we needed objective and so on and so forth. But let me drop that. We'll maybe come back to that when you go to structure. So at the end of the story, what I've done, I have used the finite elements. I have computed a bunch of the elements, the tangent stiffness, the internal force, the external force. So if this two-node truss bar element, this is like a force, internal and internal is the vector 2 by 1, and tangent is 2 by 2, tangent stiffness. So how do I now get the whole system? Because that's my interest. Well, first I established the connection between the element interpolation and the global interpolation. In other words, I had to take on my structure to enumerate the degrees of freedom. I take 1, 2, all the way to number of equations. These are unknown virtual displacement that could be dropped at the end, but they're conditioning how many equations I have. And then I have for each and every element, I have something called connectivity matrix. It simply says that the local displacement, virtual displacement number 1 and element 1 is the same as the global displacement element 1. And or basically is, well, let me maybe illustrate it here. See, this is your total mesh, and this is your two-node elements. So this one has a element 1 and 2, element 1 and 2, and element 2, and so on. But this has 1, 2, 3, and 4. Number 5 is not there. So basically, for each of these elements, there are 4 of them, I'll have to have a corresponding connectivity matrix. But the first one is the simple one. W1 local is the same as W1 global. W2 local is the same as W2 global. That's exactly matches here. However, on the case 2, W1 local is the same as W2 global, and W2 local is the same as W3 global. So basically, this one is shifted. And then to go to the third one is shifted a little bit more. And for the last one, you only have one place because there's only a place for W1, which is the same as W4, but there's no place here for W5 because this one is 0. So eliminate it. If I have a 3-node, basically I will have the same thing, only WE will be 3 by 1, and W will be still the one 4 by 1, and LE will be 3 by 4. So here they are. Basically, the first element is the simplest because W1, 2, and 3 are the same as global W1, 2, and 3. And then here, W1, 2 are the same as W3 and 4, whereas W5, there's no more place. So basically, I can write my virtual work by using element like distribution, element by element contribution with this starting element. And then I take into account that this element point of view can be expressed as the global point of view by using connectivity matrices. And I get this one. Then I take out this connectivity matrix, I slam it on the other side, and I pull out W, which is the joint to all of them. And then I recognize basically the way to assemble to get all the internal force vector by different element contribution by using this continuity matrix transpose times the corresponding internal force. And that's the same goes for the external force, whereas for the tangent stiffness, you have LE transpose times the element stiffness times LE. So you can see the size is really matching because this one is, let's say 3 by 4, and this one is like 2 by 4. So every time I'm getting my, this will be 4 by 1, 4 by 1, this will be 4 by 4 at the end, just as it should be for the case where I have 4 unknown displacement and I'm building my system. Now, the only thing which is not good in this one is basically that I have many zeros, especially if I have now hundreds of elements and I take a 2-node element, I will have only 2 components which are 1 and all the others are 0. So it's useless multiplying something with 0 when you know that nothing is going to happen. So then we kind of condense this, and this was the PhD thesis of Wilson, one of my advisors, when he wrote SAP. This was good, how you kind of reduce the size. You basically have your kind of, for each and every element, you kind of squeeze that in, and you only write the global degrees of freedom for each and every element. That is the node 1 actually have global degrees of freedom 1 and 2. Node 2 has the global degrees of 2 or 3, 3 or 4, and so forth. And here 1, 2, 3, and 3, 4 for the second mesh. And then basically you start with the corresponding product. Let's say you have an internal force vector at the node A, at the element E. You go to this global connectivity matrix at the node A, at the element E, and you take this value, you add it to the previous value, and you take it to new value. Stiffness matrix is the same, only you have an A and B, so you can take in node A and B. A could be 1, B could be 2, so you have to fish into these two together. So basically, this would really give you the chance of getting the whole thing under control and building at the end the full stiffness matrix, a full internal force vector, external force vector from these element-wise contributions. So basically, the idea is like you split, you divide, you compute each element separately, and then you kind of put it together and build your system. And then you solve it with Gaussian stuff like that. So each and every software has similar type of structure where you can get it. So in summary, what I tried to explain to you was basically first you define your problem in 1D setting with a strong form, with all the rigorous equations from mechanics, kinematics, constitutive equilibrium equation. Then you weaken one of these equations because it's easy to construct. You get the weak form. You get approximate solution by basically taking the shape functions, how you actually imagine constructing a solution. We talked about 2-node charge by element, 3-node charge by element, and so on and so forth. You end up having a matrix equation, which is a Galerkin equation, where you kick out all these free virtual displacement nodal parameters. You get a set or algebraic equation. It's either linear when it's a linear elasticity or non-linear when it's non-linear elasticity, in which case you take incremental analysis Newton method, you converge. And the role of the finite element method is really to help you build this matrix equation. You have this finite element assembly where you make it element-wise, you have a reference element, a numerical integration, and so on and so forth. So all the steps that I explained in this simple 1D setting are exactly the same in 3D setting. There are just more and more of these details, and one needs, in my mind, a little bit more efficient, let's say, notation, so you're able to kind of understand clearly that everything is under control, that all this goes into the right direction. So let me stop here and ask you if you have any questions or comments for this kind of first lecture. You know what they say when you get married: speak now or forever hold truth. Huh? Everything's fine. I wanted to do this because when I skip that, it's really